My dear students, I hope you all are really doing great. First of all, I welcome you all on this amazing platform of PhysicsWallah English channel. Students, I am quite sure you people are thoroughly enjoying this ongoing champion series, which is purely for JEE mains and NEET aspirants. Students, in this ongoing champion series, we have moved to the lecture number 6 of chemistry, and right now we are only talking about organic chemistry. So in this lecture 6, we are going to do once again a very important chapter of organic chemistry, and that is alcohol, phenols and ethers. Highly important for NEET as well as highly important for JEE mains. Students, before moving ahead, first of all, I want to thank you all for having faith in us, for believing us. Students, the content which you will be getting here will be more than sufficient for JEE mains as well as NEET. So you should not bother about the content. The content which you will be getting here, which we are providing here, is more than sufficient to crack JEE mains as well as NEET. So let's move ahead. So students, moving ahead and talking about today's goal. First of all, we'll start with alcohol. In alcohol, we'll talk about the general method of preparation of alcohol. Then we'll talk about chemical reactions of alcohol. And then the tests of alcohol. Then we'll switch to ether. Here once again we'll talk about GMP of ethers. And then we'll talk about the chemical reactions of ethers. And at the end, we are going to discuss about phenols. First, general method of preparation of phenols, and then all the important chemical reactions of phenol. So without wasting any further time, let's start our discussion for today's class. Students, let's start our discussion of this chapter with the topic alcohol itself. Alcohol are the class of organic compounds having the general molecular formula ROH, right? ROH. Now this R can be alkyl group, can be aryl group. If this R is alkyl, we'll have aliphatic alcohols, right? And if R is phenyl, then we will have aromatic alcohol, right students? And this one is nothing but aromatic alcohol referred as phenol, and this is aliphatic alcohol. This one is enol. We have studied keto-enol tautomerism, right? So in all, right? Okay. So we can have aliphatic alcohol as well as aromatic alcohol. Student, if I talk about the structure, they are having the molecular formula ROH. This oxygen is having 2 bond pair, 2 lone pair. Hybridization is going to be sp3, just like water. Right, sp3. Now student, if you look at the bond angle, in case of water the bond angle is 104.5, whereas in case of this methanol the bond angle is 108.9 degree. It's near to a perfect tetrahedral bond angle. My question to you is, why the bond angle is more here, less here? Student, in case of water, no doubt I'm having sp3 hybridization, so the bond angles would be 109.5 degree, right? But because of this lone pair, there is distortion in the bond angle, there is distortion in geometry, and because of that the bond angle is less. Now you will say, sir, here also I'm having 2 lone pair. 2 lone pair, right? But why the bond angle is more here? Student, if the central atom is same and if I am having a bulkier surrounding atom or neighboring atom, then in that case the bond angle increases. As compared to hydrogen, methyl is relatively more bulky, and because of this bulkiness the bond angle is more. Now if I talk about another class of organic compound, that is ether, here I am having 2 alkyl groups connected to this oxygen. No doubt here also I will have sp3 hybridization, 2 bond pair, 2 lone pair, right? But because of the 2 alkyl group, the bond angle will be even more as compared to methanol. So with increase in the bulkiness of the surrounding atom, The bond angle increases if the central atom is same. And in all these three cases, whether it is water, alcohol or ether, the central atom is oxygen. I hope you understood this bond angle and structure related thing. Shall we move ahead? Let's move ahead. Students, now let us talk about the classification of alcohols. There are two ways through which we classify alcohol. The first way of classifying alcohol is to which carbon this functional group OH is attached. Whether it is attached to 1 degree carbon, right? This carbon is a 1 degree carbon. Such alcohols are referred as primary alcohol. Second, whether it is attached to a 2 degree carbon like this, such alcohols are referred as secondary alcohol. If the functional group OH is attached to a secondary carbon, then it is referred as secondary alcohol, right? If the functional group OH is attached to a 3 degree carbon like this, can I say this carbon has 3 degree carbon, this one? And if the functional group OH is directly attached to this 3 degree carbon, alcohol is referred as tertiary alcohol. So I hope you understood what do we mean by the term primary alcohol, secondary alcohol and tertiary alcohol. Student, there is one more way we classify alcohol, and that is how many OH group is attached to carbon. If I am having one OH group, that is referred as monohydric alcohol. 2 OH group, dihydric alcohol. 3 OH group, trihydric. N OH group, polyhydric alcohol, right? But can you give one example of monohydric alcohol? Can you give me? Tell me. The first one, phenol, ethanol, methanol. Can I say all these alcohols are monohydric alcohol? Only one functional group OH is attached to carbon. Can you tell one example of dihydric alcohol? Yes, very common. Ethylene glycol, CH2OH, CH2OH. Ethylene glycol, dihydric alcohol. One trihydric alcohol, can you tell me? Yes, glycerol, CH2OH, CHOH, CH2OH. Trihydric alcohol. Can you tell me one polyhydric alcohol? Sorbitol, right? So, depending on the number of OH group, we classify alcohol as monohydric, dihydric, trihydric and polyhydric. Depending on which carbon it is attached, to which carbon this OH is attached, we classify alcohol as primary alcohol, secondary alcohol, tertiary alcohol. Right, students? Let's move ahead. Now, students, now let's move to the most important segment of today's class, and that is general method of preparation of alcohols. We can synthesize alcohol from n number of organic compounds. Starting from alkene, we can even synthesize alcohol from alkyl halides, carbonyl compounds and acids and acid derivatives. So let's discuss the GMP of alcohol one by one. First one, from alkenes, by acid catalyzed hydration of alkenes. Students, we have studied alkenes undergo electrophilic addition reactions. And in this electrophilic addition reactions of alkene, we have studied several methods through which we can synthesize alcohol. I hope you remember it. In the last class only we have studied it in the hydrocarbon, right? Okay. Acid catalyzed hydration. Okay. I'm having an alkene like this, RCH, double bonded CH2. Right? And now it's treated with an acid H plus / H2O. Acid catalyzed hydration. Or I can take dilute acid, dilute H2SO4, or I can take any dilute acid. The first step is the formation of carbocation. This H plus will attack on alkene and I will have the formation of RCH3 positive. The carbocation once formed may undergo rearrangement to give a more stable carbocation, and on the rearranged carbocation, rearranged carbocation, this water will attack to form alcohol. Right, student? I hope you understood this one. First, I am having an alkene. This alkene is treated with H plus in the presence of water, or I can even take any dilute acid which is a source of H plus. This H plus will do electrophilic addition reaction on alkene. I will have the formation of carbocation, and on the most stable carbocation, this water will attack to form alcohol. I hope you understood this one. Okay, let's do one question related to this one. I'm having an alkene, and this alkene is treated with H plus / H2O. Students, first step, I will form the carbocation. Now this pi bond will break. Either I can form carbocation here, or I can form carbocation here. Which carbocation is more stable? This one. The positive charge on second carbon, right? Okay, so here I am going to form this carbocation. Right, student? Now, this carbocation will undergo rearrangement. Why will it undergo rearrangement? The answer is, I am having a 5-member ring. Just outside this ring, I am having a positive charge. So it will undergo ring expansion to give me a more stable carbocation, right? And now, I will have the migration of this alkyl group, and then I will have the formation of a more stable carbocation like this. Let's see how I do ring expansion. Most of the students even get confused here also. Now, and this one, right? And now can I say, student, this particular bond, let's name it a 1, 2, 3, 4, 5, 6. So this 2,6 bond is cleaving and it is migrating to, it's getting connected to 1,6, right? So can I simply connect this bond over here? Now it's 1, 2, 3, 4, 5, 6, and on the carbon number 2, I'm having positive charge because this particular carbon is losing one bond, right? Okay. Now can I draw it in a better way? I'm having a 6-member cyclic ring, right, student? On carbon number 1, I'm having a methyl group, and on carbon number 2, I'm having a positive charge. Is the carbocation formed? Is it the most stable carbocation? The answer is no. Still it will undergo further rearrangement, right? Okay. I will do one hydride shift from here. This hydrogen will migrate here, and I will have the formation of positive charge at this particular carbon. Now here water will come, H2O will attack on this carbocation, and I will have a formation of 3-degree alcohol, right? So this is my final product. I hope you understood this particular question. Please copy it. Students, now let's move to the next method of preparation of alcohol. Oxymercuration and demercuration process. This particular process also we have studied in the previous lecture only, right? So it's all about revision of previous lecture. I'm having an alkene RCH, doubly bonded CH2. I hope you remember it, right? It's treated with HgOAc twice. Then water as a solvent. First step, this is nothing but OM step, oxymercuration. Then we do demercuration, NaBH4, right? This step is DM step. What will happen in the first step? The attack of HgOAc, formation of a 3-member cyclic ring. Water will attack on the more substituted carbon. No rearrangement because no carbocation is formed here. Right? I am having a 3-member cyclic ring, a non-classical carbocation, so no rearrangement. Water will attack on the more substituted carbon from the backside. So if I talk about the OM step, can I say in the OM step, the product which we get with is RCH, OH, CH2, HgOAc, right? I hope you remember this one. Is it clear, students? Now, the next step is the DM step. We treat this substrate with NaBH4. The function of NaBH4 is to remove this CHG bond and substitute it with CH bond. So I will have the formation of R, CH, OH, CH2, H here. Right, students? So this is the final product which we will get here. This particular process is referred as oxymercuration-demercuration. First, oxymercuration, and the next step is attack of NaBH4, and this step is demercuration. The most important thing which we have to keep it in mind, first, anti-attack stereo-wise, regio-wise, no rearrangement. Simply the nucleophile will attack on the more substituted carbon. That's it. The nucleophile will attack on the more substituted carbon. Right, students? Let's move ahead. Let's do this particular question. A very, very important question. I'm having a 3-degree carbon, and this is the alkene part. First step, OM step, and then DM step. Shall I write the product directly? Yes. Do we have rearrangement here? No. Why? Because there is no carbocation. The carbocation which we get here is basically I am having a non-classical carbocation, a 3-member cyclic ring, right? So it won't undergo rearrangement. The partial carbocation is formed here. Am I clear, students? Okay. No rearrangement. Now, the nucleophilic part is the OH part from here and H part from here. This H will get attached to the less substituted carbon, and this OH will get attached to the more substituted carbon from backside. You can see, right? Okay. So the product which I am going to write is CMe, Me, Me. Then we'll have CH, OH, CH2, H. This H and OH are at anti-position with respect to each other. Am I clear? Let's move to the next question. Once again, okay. I'm having OM in the first step and DM in the next step. Okay. So students, from here, I will have OH, and from here, I will have H. This H will attack on the less substituted carbon, and the OH will attack on the more substituted carbon, and they will be at anti-position with respect to each other. No rearrangement of carbocation because no carbocation is formed here. I will have methyl OH group getting added here. Let's suppose this OH is on the wedge dash. Now this hydrogen will get added on that wedge, just in order to show you the stereo of this product. I hope you understood this. So oxymercuration-demercuration, sort of Markovnikov addition, but no rearrangement, anti-attack stereo wise. I hope you understood this one. Let's move to the next one. Hydroboration-oxidation process, anti-Markovnikov addition, right? Okay, we have studied this reaction also in alkene. Even we have studied about the mechanism also. I was having a 4-member cyclic transition state, right, students? Formation of a trialkyl borane, and the next step was oxidation process, H2O2 OH minus. The first step is addition of borane, right? Finally, let's talk about the product. Syn addition. Syn addition. What do we mean by syn addition? Both H and OH will get added on the H and OH will get added on the same side. Second, anti-Markovnikov. Anti-Markovnikov. What do we mean by it? Here, the nucleophilic part will attack on the less substituted carbon. So if I am having RCH-CH2, so OH will get attached here and H will get attached here from the same side. right? This particular process is referred as hydroboration-oxidation reaction. I hope you understood this one also. Let's move ahead. Let's do these questions in order to understand it in a better way. BS3THF H2O2/OH minus. Students, from here I'm going to add one OH. From here I'm going to add one H. This H will get attached to the more substituted carbon here, and this OH will get attached to the less substituted carbon from the same side. Okay, let me put it like this. This OH will get attached to the less substituted carbon from same side. So the product which I am going to get is CMe, Me, Me, CH, H and CH2OH. You can see here both H and OH, they are on the same side. Am I clear, students? Okay, let's do this particular question. Can you do it? Please do it fast. Source of H, source of OH, OH on the less substituted, H on the more substituted from the same side. So both H and OH will be there on the, if H is there on the wedge, OH will also be there on the wedge part itself, right? I hope you understood this one also. Please copy it. I hope you have copied it, right? So shall we move ahead? Okay, let's move. From alkyl halides by nucleophilic substitution reaction. This one we have also studied. SN1, SN2. The third lecture itself, reaction mechanism, right? Okay. So whatever we have studied is basically the revision of previous lectures, right? Okay. By SN2 mechanism. SN2 mainly occurs in 1 degree alkyl halide and 2 degree alkyl halide. So if I am having an alkyl halide like this R can be either 1 degree or preferably 1 degree, less preferably 2 degree, and if it's treated with a strong nucleophile, let's suppose KOH, in a polar aprotic solvent like DMSO, student, in that particular case, simply the halogen will get replaced by OH and I will have formation of either 1 degree alcohol or 2 degree alcohol. One more thing, in SN1, in SN2 reaction, the product, if I talk about this, stereo-wise will have inverted product. If this X is on wedge, then this OH will be on the dash part. Okay, am I clear, students? If this halogen is on wedge, it will be on dash. If halogen is on dash, alcohol attached will be on the wedge. But it only occurs in SN2. For SN2, we should have either 1 degree alkyl halide or 2 degree alkyl halide. The solvent taken should be generally polar aprotic, right? Okay, do we have rearrangement anything? No rearrangement. Why? No formation of carbocation. This reaction is a single step process, only in transition state, so no rearrangement, simply replacement of this X or substitution of this X with OH group. Let's move ahead. Second, we can prepare 3 degree or secondary alcohol through SN1 mechanism. If I am having a 2 degree alkyl halide or most probably 3 degree alkyl halide like this, C, R1, R2, R3, X. Can I say this alkyl halide as a 3 degree alkyl halide? Alkyl halide, and now if it's treated with polar protic solvent or a weaker nucleophile or weak to moderate type of nucleophiles, generally neutral nucleophile, and the best one is water. So if I am having a 3 degree alkyl halide and if it's treated with water, First, this halogen will depart, CX bond cleavage, formation of carbocation. Once the carbocation is formed, it will undergo rearrangement to give a more stable carbocation, and on this most stable carbocation, this water molecule will attack from the front side as well as from the back side. So how many products will get? 2 products. They will be the mirror image of each other. Why 2 products? Because here I am having the formation of carbocation. The nucleophile may approach from the front as well as from the back, right? Okay. So let's write the product. R1, R2, R3, OH. So if I am having 1 degree alkyl halides, we'll get alcohol, primary alcohol through SN2. If I am having 3 degree alkyl halide, we'll get 3 degree alcohol through SN1. If I am having 2 degree alkyl halide, here both SN1 and SN2 can occur. Now depending on the nature of nucleophile, if I am having a strong nucleophile, in that case SN2 will occur. If I am having a weak or moderate type of nucleophile, in that case SN1 will occur. Am I clear, students? So shall we move ahead? We have discussed all these things. It's basically a revision of previous classes, right? Okay, let's move ahead. Let's solve these 2 to 3 questions. I'm having a 2 degree alkyl halide. Nucleophile OH minus. Anionic nucleophiles are generally a strong and better nucleophile. The solvent is polar aprotic. If I'm having aprotic solvent and a strong nucleophile, simply I will have SN2 reaction, inversion. If Br is on the wedge, OH will be on the dash. So the product will be like this, right? Okay. Next one. Once again, 1 degree alkyl halide, right? This carbon is a primary carbon, 1 degree alkyl halide. No doubt there is crowding, but the solvent and the nucleophile. Solvent is DMSO and the nucleophile is a strong nucleophile. It will simply attack here, will replace it, and I will have the formation of OH. Right. Now, I'm having a 2 degree alkyl halide, right? And it's treated with a weak type of nucleophile. So which reaction? I will have SN1 reaction occurring here. So what is there in the first step? Ionization. First, the Cl will depart and I will have the formation of this carbocation. Right, students? Okay. Now, is it the most stable carbocation? The answer is no. So will it undergo rearrangement? Definitely yes. Okay. I'm having a carbocation like this. Right? Okay. Will it undergo expansion? Definitely yes. Let's do the expansion. 1, 2, 3, 4, 5, 6. Now, which bond we should cleave? 2, 3 or 2, 6? That bond will cleave which is having more nucleophilic character, or we can say which is having more electron density, right? Then it will have a better donation ability. 3 degree is having a better migration ability as compared to a 2 degree, right? So I'm going to cleave this particular bond. Okay, so this bond is going to migrate. This bond will shift here. Now, let's see. Really important question. I will have, right, students? Then, okay, and now this 2,6 bond is cleaving. Here at 6th carbon, I am having this methyl group also, and this is carbon number 1, and here I will simply connect it with this one, right? Now I am having 2, 3, 4, 5, 6. On 2nd carbon, I will have a positive charge, right? So here I am going to draw a positive charge. Now let's draw it in a better way. 6-member cyclic ring. On 1st carbon and 6th carbon, I am having a positive charge, and here I I'm having a methyl on carbon 1, 2, 3, 4, 5, 6. And positive charge on carbon 2. Now let's do the migration of hydride. Hydride shifts to form a 3-degree carbocation, right? Okay. So now I'm going to have a carbocation like this. Now on this particular carbocation, my nucleophile H2O will come. It will attack over here from the front side as well as from the back side. One of the product I'm going to write, my final product, it's nothing but OH over here and this one, right? I hope you understood this particular question also. So shall we move ahead? Let's move ahead, student. Now students, we can synthesize alcohol by using a very important organometallic reagent, and that's nothing but Grignard reagent. The general formula RMGX. R is having negative, MGX positive. This Grignard can act as a base as well as nucleophile. The question is when it will act as a base. If Grignard is treated with a compound having acidic hydrogen. If Grignard is treated with a compound and if that compound does not have any acidic hydrogen, in that case it will behave as a nucleophile and will do nucleophilic attack. Am I clear? Okay. Addition of Grignard reagent to ethylene oxide gives a primary alcohol with 2 carbons attached. Okay. Student, I am having an epoxide ring. CH2, CH2O, right? This is epoxide. On this epoxide, let me treat CH3MgBr. Let us try to understand it in a better way. CH3MgBr, can I say this carbon will have a negative character and MgBr will have a positive character, right? Now, this CH3 minus, what it will do? It will do the nucleophilic attack. Why not the basic one? Because here we don't have any acidic hydrogen. The hydrogen is connected to carbon, right? Less electronegative atom. So no acidic hydrogen. Now it will attack on the less substituted carbon. Although in this particular case, both the carbon have same degree of substitution. So this CH3 minus will attack on any of the carbon. Let's suppose it's attacking on this carbon. As soon as it attacks here, this bond will cleave. This CH3 minus is approaching from the back side. So I will have CH2, CH3. Now this bond is cleaving. So here I will have CH2, O minus, right? Next step, take water, acidified water. What this water will do? Will protonate this O minus. Or I can take H plus slash water. It will protonate this oxygen and I will have the formation of CH3, CH2, CH2, OH. Right? So this is how we attack on a 3-member cyclic ether or a 4-member cyclic ether. Generally, mainly we prefer 3-member cyclic ether to form alcohol. Let's do this particular question in order to understand this particular reaction in a better way. I am giving you 45 seconds. Please try to solve it on your own. Once you are done, please mention in the comment box and then we'll do it. Students, I hope you are done with this particular question. So let's discuss this. I'm having a 3-member cyclic ether, right? Epoxide ring. And it's treated with Grignard in the first step. CH3 minus OMgBr plus. Now this CH3 minus will act as a nucleophile. The region is no acidic hydrogen. Now this CH3 minus will attack on less substituted carbon. It will preferably always attack on less substituted carbon. So between this carbon and this carbon, what do you say? Which one is less substituted? This one. So it will attack on this particular carbon. As soon as it attacks over here from the back side, this bond will cleave. So I will have the formation of CH3, CH2, CO negative, CH2, CH3. This O negative will form bond with MgBr, right? So O negative, MgBr positive. The next step is reaction with water. Simply this O negative, OMG bond is relatively weaker, right? Ionic will easily cleave, and I will have the formation of CH3, CH2, COH, right? CH2, CH3. Right, students? I hope you understood this one also. So shall we move ahead? Let's move ahead. Now, from carbonyl compound, it's time to discuss the general method of preparation of alcohol from carbonyl compounds. Can we say this carbonyl compound is the oxidized product of alcohol, right? If I'm having a primary alcohol, the oxidized product is aldehyde. If I'm having 2-degree alcohol, the oxidized product is ketone. So if I'll do the reduction of carbonyl compound, I am going to get either primary alcohol, secondary alcohol, or even sometimes 3-degree alcohol. Let's talk about this. Reaction of nucleophilic addition to the carbonylic groups by Grignard reagent. Once again, this Grignard is there. Okay. Highly important organometallic reagent, right? Okay. So, I'm having RMgX. This RMgX is treated with a carbonyl compound. R is having a negative character, MgX positive character, right? Now this R minus will behave as a nucleophile, will do nucleophilic addition reaction on this carbonylic carbon. As soon as it attacks over here, this alkyl group will get attached to the carbonylic carbon. The double bond will shift, it will migrate, oxygen will have negative charge, and in the next step it will simply take H plus from water, will form alcohol. Okay, let me take one example so that you can understand it in a better way. I'm having CH3, C double bond O, H. One aldehyde is there, right? This is aldehyde. And now it's treated with CH3, MgBr. CH3 negative, MgBr positive, right? Okay. Now, what this CH3 will do? It will attack on this carbonylic carbon. Why? Because it is having a slight positive charge. As soon as it attacks over here, this particular double bond will shift on oxygen. I will have the formation of adduct like this. O negative, CH3 over here and H over here. You can attach this MgBr to this oxygen, right? And next step is all about the protonation. Attack of H plus from water and formation of CH3, CH3, OH and H, right? I hope you understood this particular mechanism. Please copy it. Students, I believe you might have copied it. So shall we move ahead? Tell me. Shall we move ahead? Yeah, let's move ahead. Let's do these questions. I'm having aldehyde and it's treated with a Grignard pH MgBr. Here I will have pH negative. This pH negative will act as a nucleophile, will attack on this carbonylic carbon. This double bond will shift to this oxygen. In the next step, H from here will attack here, right? Simple. Add the alkyl part of Grignard to the carbonylic carbon and H plus from water to oxygen. Remove this double bond. As simple as that. Okay, so the product which I am going to get is CH3, CH2, COH, pH, and H, right? Okay, move to the second reaction. Here I am having ketone, and ketone is treated with Grignard part. Okay, so here CH3 CH2 negative, this one positive. This alkyl part will attack on the carbonylic carbon. As soon as it attacks over here, the pi bond will shift, and I will have formation of CH3O negative, CH3, and here ethyl part, that is ET, O negative MgBr, right? Next step, water form CH3 COH, CH3 and ET. Now let's have a look at the product. If I'm having ketone as a substrate and if it's treated with a Grignard reagent, the product which I am going to get is a 3-degree alcohol, tertiary alcohol, right? You can see here 3-degree alcohol. If I'm having aldehyde as the substrate and then if it's treated with a Grignard reagent, the product which I will get is a 2-degree alcohol. Right, students? Aldehyde on reaction with Grignard gives secondary alcohol in general. If I am having ketone, in general we will get a tertiary alcohol. Right? So generally we synthesize tertiary alcohol from ketones using Grignard reagent. This is the one of the methods through which we synthesize 3-degree alcohol. Let's move ahead. Students, moving ahead, now we are going to treat the Grignard reagent to acid derivative, and from acid derivative I am going to generate alcohol. How does this reaction occur? Let's see. I am having a ester. I can generalize it. Let's write the general reaction. I am having RC double bond O G, and now this G can be OR. If it is OR, then I will have ester. It can be X. It can be OC double bond OR. Any of these three acid derivative. RC double bond O OR, RC double bond OX, or RC double bond O OC double bond OR. If it is OR, ester, X acyl halide, and OC double bond OR, anhydride. Any of these acid derivative. If it is treated with Grignard, first I will have the formation of ketone. How? Let's see. See, if it's treated with a Grignard, this Grignard is having a nucleophilic behavior, right? Now this R minus will come and will attack on this carbonylic carbon. As soon as it attacks over here, this pi bond will shift to the oxygen, right? Now I am having the formation of RC O negative, R and G. Now student, what will happen? This G is a good leaving group, or we can say a moderate type of leaving group. This O negative will do internal attack and G will have to depart. Right? Okay. As soon as it is departed, I will get RC double bond O R, means ketone. So if I am having an acid derivative and if it's treated with Grignard, the first product which I am going to get is ketone. Now this ketone on further reaction with Grignard is going to form a 3-degree alcohol. You can see here also I am having ester, right student? This ester is treated with Grignard R2MgX. This R2 is attacking over here. I am having the formation of an intermediate. O negative is back delocalizing. This is the leaving group G. This G will get departed. I will have a formation of ketone. Now you may say, so why this group is departing? If you look at this carbon, it is having a tetrahedral geometry. It is having a planar geometry. A planar geometry is having more spacing, more stability. That's why a tetrahedral geometry is getting converted to a planar one. Finally, with the attack of Grignard again, once again it is getting converted to tetrahedral. Now it does not have any other option. But if it is having a good leaving group, then definitely it will get departed to form a planar geometry. right? So first I'm having a formation of ketone, and this ketone is further treated with Grignard to form a 3-degree alcohol. Students, always remember, whenever I am having an acid derivative, if this acid derivative is first treated with Grignard, I will have the formation of ketone. Ketone on further reaction with Grignard will give me a 3-degree alcohol. Acid derivative, Grignard. First, ketone on further reaction with Grignard, formation of tertiary alcohol. Shall we move ahead? Let's move ahead. Okay, I'm giving you one example. Let's do it. I'm having CH3 C double bond O Cl, and it's treated with pH Mg Br 2 mole. Okay, and first step, and next, simply in all the step you have to take water. Okay, student, I'm having acyl halide as my substrate. This is nothing but acyl halide, and this acyl halide is treated with a Grignard reagent, pH negative MgBr positive. This pH negative will come and will do nucleophilic addition on this carbonylic carbon. As soon as it attacks on this carbon, this pi bond will shift over here. I will have the formation of CH3 C pH O negative MgBr positive Cl. Now this O negative will undergo back delocalization, and Cl has to depart, right? I will have the formation of CH3 C double bond O pH. I'm having one more mole of Grignard, that is pH MgBr. It's further treated with pH MgBr. This pH will have a nucleophilic behavior, will attack over here. As soon as it attacks over here, this pi bond will shift here. I will have the formation of CH3 C O negative pH. In the last step, it is treated with water. This O negative is going to take H plus from water, and I will have formation of a 3-degree alcohol, right? I hope you understood how do we synthesize alcohol from acid derivative. First, treat it with Grignard, form ketone, treat it with Grignard once again, and you will have the formation of a 3-degree alcohol like this. Please copy it, students. So shall we move ahead? Tell me. I hope it's crystal clear. Let's move ahead. By reduction of carbonyl compound, student, if we do the catalytic hydrogenation of carbonyl compound, if I treat a carbonyl compound with H2 in the presence of transition metals like Ni, PDPT, in that case also we will get alcohol. If I am having aldehyde as a substrate, and if it's treated with H2Ni, that is catalytic hydrogenation, I will have formation of primary alcohol, 1-degree alcohol. If I am having a ketone R, C, double bond O, R dash, unsymmetrical ketone, and if it is treated with H2Ni, what you need to do? Add 1H on this carbon, 1H on oxygen, remove this double bond, simple, R, C, OH, R dash, H. I have simply cleaved this double bond, right? I have added one hydrogen over here, one hydrogen over here, one hydrogen over here. Ketone secondary alcohol, aldehydes primary alcohol on catalytic hydrogenation, right? Let's move ahead. Students, talking about the reduction of this carbonyl compound, we have some metal hydrides, and these metal hydrides also reduces carbonyl compounds to alcohol. The best one is lithium alumino hydride, and the second one sodium borohydride. LH, lithium alumino hydride, that is LiAlH4, and second one SBH, sodium borohydride, NaBH4. Let us first of all talk about LiAlH4. if I talk about the GMP of this LiLH4, it is prepared by treating lithium hydride with AlCl3. Student, if I am having LiH and if it is treated with AlCl3 in the presence of solvent, you are going to get LiAlH4. Now if I talk about this metallic hydride, it's an excellent reducing agent, excellent source of H minus. Okay, it's a source of H minus. Now what this H minus will do? It will do nucleophilic attack on the carbonylic carbon. Okay, and then it will reduce the carbonyl compounds, acids, and even acid derivatives to alcohols, right? Let's talk about one by one. Okay, student, I'm having LiAlH4, and if it's treated with aldehyde, one by one I will talk about. I'm having aldehyde RC double bond OH treated with LiAlH4. AlH4 first, and solvent, let's suppose water. What you need to do, this LiLH4 is a source of H minus. This H minus will attack on the carbonylic carbon. As soon as it attacks, this bond will shift. Now O negative. So from here H plus will come and it will attack on oxygen. So the H minus coming from LiLH4 will attack on carbonylic carbon, and H getting attached to oxygen will come from solvent. The product which we will have is RC. Already one hydrogen was there, one hydrogen coming from LiLH4 and OH. So 1 degree alcohol, right? Now, if I am having ketone, RC double bond O R dash, and if it is treated with LiAlD4, okay, and second H2O, can you tell me the product? Can you tell me the product here? Please tell me fast. Student, this LiAlD4 is a source of D minus. This D minus will do nucleophilic attack on the carbonylic carbon. As soon as it attacks, this bond will shift over here. RC D O negative R dash. Now H2O, source of H plus. This H plus will attack on oxygen. I will have RCOH R dash and D. Now 2 to 3 more different. I am having RC double bond O OR dash. LiLH4 is even able to reduce all the acid derivatives also, like carboxylic acid, esters, acyl halides to alcohol. Okay, I'm having LiAlH4. LiAlH4, I'm having ester and it's treated with LiLH4 in the first step, and next step it's treated with water. What you need to do? Simple. I'm giving you a shortcut. Cleave this bond, add one hydrogen over here, okay, and then reduce this aldehyde to primary alcohol. So you will have the product as RCOH, right? From here I was having aldehydes, and this aldehyde is reduced to 1 degree alcohol, and now this RO part is getting converted to alcohol R-OH. Student, if I am having acid and acyl halides like this, RC double bond O OH or even X, and now if it's treated with LiAlH4, in that case I will have simply the formation of RCH2OH, right? I hope you understood the reducing action of LiAlH4. Now students, if I am having a nitrogenous compound like amides, nitryls, oxymes, in that case if I treat these compounds with LiAlH4, we will not get alcohol. In that case we will get amines. We'll talk about that in the next chapter. Now let's talk about the next reducing agent, and that is NaBH4. Now someone may say, which is a better reducer? Student, if I talk about LiAlH4, there I am having AlH bond. If I talk about sodium borohydride, that is NaBH4, I am having BH bond here. Right? Okay. AlH bond and BH bond, which is a stronger bond? 1s 2p. 1s 3p. Extent of overlapping is much better in 1s 2p as compared to 1s 3p. Right? So BH bond is a stronger. And if it's stronger, it's tough to clear. So can I say it's an excellent source of H minus? So in general, LiLH4 is a better reducer as compared to sodium borohydride, right? That's why sodium borohydride is not able to reduce all acid derivatives. Okay, let's talk about the reducing action of this particular metallic hydride. If I'm having aldehyde, if this aldehyde is treated with NaBH4, I will have primary alcohol just like LiAlH4. If I am having ketone, this ketone on treatment with NaBH4 will give me secondary alcohol, right? Just like LiLH4. So both LiLH4 and NaBH4 reduces aldehydes and ketones in the same way. Let's do these questions. This NaBD4 is a source of D minus. What this D minus will do? Will act as a nucleophile and will do the nucleophilic addition with carbonylic carbon, right? So this D minus will come, will attack over here. This pi bond will shift. I will have RCO negative, R dash, and then D. In the next step, I am having water as a solvent, source of H plus. H plus will get attached from here, right? So this is the product. Here I am having D. You need to focus on this D. Okay. Now, NaBH4, it's treated with a compound containing keto group, acyl halide, and ester. Student, NaBH4 reduces aldehydes, ketones, and acyl halide. It is unable to reduce carboxylic acid, esters, and hydrides. All these compounds does not react with NaBH4. Am I clear? It is unable to reduce carboxylic acid, esters, and anhydrides. Okay. Now let's focus on this particular question. This is acyl halide. It will get reduced, and it will get reduced to alcohol. Ketone to alcohol. Ester will remain as it is. So I will have, right, ester remaining as it is, ketones to secondary alcohol, and this one also, CH2OH, right? I hope you understood this one. Acyl halide, simple, treated with RC double bond OX, treated with NaBH4. You need to do one thing, simple. Remove this halogen, okay, replace it by hydrogen. Add one hydrogen on this oxygen also. So I'm having RCHHOH, right? CH2OH. I hope it is crystal clear. Please copy it. There is one more technique through which we can synthesize alcohol from carbonyl compound, and that is Blanc reduction method. Students, here I am having carbonyl compounds or acid derivatives and mainly ester. Carbonyl compounds, aldehyde ketones, and ester. Whenever treated with alkali metal like sodium in the presence of alcohol, this metal in the presence of alcohol is a source of hydrogen, and this hydrogen will do the reduction of carbonyl compounds. So if it's aldehyde, we will have alcohol as the product, primary alcohol as the product. If it's ketone, we will have secondary alcohol, and even students, it's able to reduce esters also. Like RCO2R2. In this case, we'll get a mixture of alcohol, right? Let me explain you. R, C double bond O, or let's suppose R1, O, R2. If this ester is treated with Na in the presence of ethanol, metal in the presence of alcohol, whenever alcohol is treated with metal, you will get hydrogen. We'll discuss this in this particular chapter only. Now this hydrogen liberated will do the reduction of this ester. So the product which I am going to get is RCH2OH plus R2OH. Although it occurs by a different mechanism, sodium basically undergo oxidation, but the mechanism here is not that important. Okay, you simply need to remember carbonyl compounds treated with metal in the presence of alcohol generates alcohol. Okay, it reduces aldehydes to primary alcohol, ketones to secondary, and even it reduces esters also. Let us move ahead. Next one, students, amines. If amines is treated with NaNO2 plus HCl, whenever this NaNO2 plus HCl combines, we get nitrous acid, that is HNO2. 1 degree of primary amines, whenever treated with HNO2, we get a very important compound referred as diazonium, Rn2 positive. Okay, now this N2 positive is a very good leaving group. We have studied this, right, in reaction mechanism. It will have a tendency to depart. As soon as it departs, I will have the formation of carbocation. This carbocation may undergo rearrangement, and finally on the most rearranged carbocation, water will attack and I will have the formation of alcohol. So students, I'm having amine, primary amine. This is primary amines. This primary amines, whenever treated with HNO2, OH, H, O, N double bond O. Amines on treatment with this one forms, first of all, it is going to form Rn triple bond N positive, diazonium. This N2 will have a tendency to depart. It's one of the best leaving group. As soon as it departs, I will have the formation of carbocation, and on this carbocation, water molecule will attack. I will have the formation of alcohol, and along with this, nitrogen gas is liberated. Okay. Student, let's solve some question in order to understand this reaction in a better way. I'm having CH2NH2. Okay, now this is treated with HNO2. So can I say first I will have the formation of Me, hydrogen, CH2, N2 positive. It will depart. As soon as it departs, I will have the formation of carbocation, but the carbocation formed is a 1 degree carbocation, highly unstable. It will undergo rearrangement, right? Now methyl and hydrogen, which one is having a better migration ability? Hydrogen. Why? Because having higher electron density. So this hydrogen will migrate over here. I will have the formation of a more stable carbocation, C positive, Me and Me. Here also I will have CH3 now, CH2 and H, CH3, and on this carbocation water molecule will attack. I will have the formation of C, OH, Me, Me and Me. I hope you understood this one. Let's move to the second one. Students, here I am having a nitro group, right? This nitro is treated with Fe plus HCl. Whenever I am having nitroalkane, and if it's treated with metal in the presence of acid, whether it is Fe plus HCl, Sn plus HCl, we will get NH2. Nitro will get converted to amines. Now this amine is treated with HNO2. NaNO2 plus HCl is nothing but HNO2, right? Now amines on reactions with HNO2 is going to form diazonium. Shall I write the direct product B itself? Okay. So I'm going to write here, I'm having a 6-member cyclic ring. Here I'm having a methyl group. Here I will have N triple bond N positive. This one will act as a very good leaving group. It will have a tendency to depart. Formation of a 2-degree carbocation will undergo a rearrangement. I will have the formation of 3-degree carbocation. Now on this 3-degree carbocation, alcohol will attack and I will have the formation of a 3-degree alcohol. Right, students? I hope you understood this one also. Please copy it. Now, let's talk about few more methods through which we can synthesize alcohol. Till yet, mainly we were talking about the formation of monohydric alcohol. What do we mean by monohydric alcohol? The compound containing single OH group, right? It's time to discuss about dihydric alcohol. Dihydric alcohol means 2 OH groups are connected to this organic compound. And the best way to synthesize dihydric alcohol is to react an alkene with dilute cold KMnO4. That is Bayer's reagent, right? Okay. Converting an alkene to glycol requires adding hydroxy group to each end of the double bond. This addition is referred as hydroxylation. The best reagent is either Bayer's reagent, cold dilute 1% KMnO4, alkaline KMnO4, or I can use OSO4. Both of them will have the same function. Both of them will have the same function. I will have the formation of vicinal diol. Vicinal diol. Now what do we mean by the term vicinal diol? 2 OH on the adjacent carbons, on neighboring carbons. Such a system is referred as vicinal diol system. 2 alcoholic groups on the adjacent carbon. Right, students? Now, if I talk about this particular reaction, first we will have a formation of vicinal diol system. Then, if I talk about stereo-wise, this reaction is a syn addition reaction. Syn addition. What do we mean by syn addition? Both OH will get added on the same side. Both OH will get added to the same side of the doubly bonded carbon. I'm having a doubly bonded carbon C double bond C. It's either treated with OSO4 in the presence of H2O2, or if it's treated with KMnO4 in the presence of OH minus, that is alkaline KMnO4. In both the case, I will have the formation of vicinal diol. Both OH group will get added to the adjacent carbons. That is the carbon containing the double bond. I'll break this double bond. I'll add 2 OH on these 2 carbons, and the addition will occur from the same side. Okay. Now, student, please attempt this particular question. We have studied this electrophilic addition reaction, right? And stereochemistry also we have studied. If I am having a trans alkene and if I do syn addition, which type of product I am going to get. If I am having a cis alkene and if I do syn addition, which type of product I am going to get. We have studied that, right? Please do it. Cold KMnO4, syn addition, both the OH will get added on the same side. Please do it. Now, which type of alkene is this one? Can I say trans? Right? KMnO4OH minus, which type of addition will it perform? Syn addition. Syn addition, right? Trans plus syn. In this particular case, we are going to get a trio system, or we can say a DL mixture, right? Okay, so I'm going to draw the Fischer one. CH3 here, CH3 here. Trio means 1 OH here, 1 OH here, H and H. We won't have plane of symmetry. So I will have one more product, DL mixture, right? DL mixture. The second one, I'm having a cis alkene, right? Alkene is cis, addition is syn. Cis plus syn. erythro system, right? Or we can say it as a meso compound. Here both OH will get added on the same side. Is the product optically active or inactive? The product is optically inactive. This one optically active. I hope you understood these two questions. Shall we move ahead? Let's move ahead. Anti-hydroxylation using per acids. What do we mean by the term per acids? We studied this, right? In the previous class also. Whenever alkene is treated with per acid, we have the formation of epoxide, 3-member cyclic ring, right? I hope you remember it. Per acid, R, C, double bond O, 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 H. This is one additional oxygen, right? And what this oxygen will do? It will form a 3-member cyclic ring with alkene, right? So if I'm having a alkene cyclopentene, if it's treated with per acid, any per acid, let's suppose this one, CH3, C double bond O, double O, O, H. What it is going to do? Simple remove one oxygen from here and form a 3-member cyclic ring, that is epoxide ring. Okay, now I'm having a formation of 3-member epoxide ring on this cyclopentane. Now let us suppose it's treated with H plus slash H2O. What this H plus will do? Whenever you see oxygen and H plus, do the protonation of oxygen. So what you will do? You will simply attach this hydrogen to oxygen. You will have a formation of 3-member cyclic ring, and this ring is having a positive charge, oxonium ion formation. Now the role of nucleophile will come into picture. This H2O will attack from the back side. This bond will cleave, and I will have the formation of one OH on this carbon and one OH on this carbon. Stereo wise, they will be at anti-position. One OH on the wedge, one OH on the dash. So students, if I need to synthesize vicinal diol, we can have two different reagents. Either cheminophore OSO4, one, but there will get syn-vicinal diol. And if I need anti-vicinal diol, in that case, we need to use per acid. I hope you understood it. Please copy it. Have you copied it? Okay. Now, I'm having alkene and it's treated with a per acid, and this is performic acid, PFA. Formic acid, one more formic acid with one extra oxygen in free, that is performic acid, right? Formic acid with one free oxygen is performic acid, and it's treated with H plus slash H2O. First, I will have the formation of 3-member cyclic ring, that is epoxide ring. Let me form that. I'll break this double bond. It will remain as it is, and now I will have this one. Next step, this epoxide is treated with acidified water, protonation of oxygen, oxygen having positive charge, attack of water, where whenever I am having a cyclic ring and that ring, if it is having a positive character, nucleophile attacks on the more substituted carbon from the backside. I am having a cyclic ring. If the cyclic ring is having a positive charge, nucleophile attacks or approaches from the backside, and regio-wise it attacks on the more substituted carbon. Okay. So this H2O will come and it will attack from the backside on the more substituted carbon. This bond will cleave. I'll have the formation of, right, OH, and here OH, both the OH at anti position with respect to each other. Right, students? Okay. Next one. I'm having a trans alkene. And here, which type of addition we will have? Trans addition, that is anti-addition. Trans on anti-addition will give me erythro system or a meso system. So I will have simply CH3, HOH, HOH, CH3. This is a meso one. Trans plus anti, meso. Trans plus syn, DL. Cis plus syn, meso. Cis plus anti, DL. Am I clear? Please comment. Students, now it's time to discuss the chemical properties of alcohol. Alcohol mainly performs two types of reaction. Okay, let's see. If I look at the structure of alcohol, it is having a formula ROH. Okay. Now it mainly undergoes two types of reaction. Type 1, that is type 1, and the other one is, let me write as type 2. What happens in type 1? I'm having ROH. Student, in type 1, we observe ROH, we observe OH bond cleavage. And when I will have OH bond cleavage? If alcohol is treated with any base. So type 1 is basically acid-base reaction. Acid-base reaction, when alcohol is acting as an acid, it is having a tendency to release H plus, and this alcohol is treated with a strong base. So type 1 is all about acid-base reaction. Alcohol acting as an acid, treated with a base, we will have the formation of RO minus, alkoxide ion. Okay, this H plus will be snatched by a base. So if it's an acid base reaction, I will have OH bond cleavage. One more reaction is shown or exhibited by alcohol, and in that case, in that particular case, students, we will observe mainly RO bond cleavage. Okay. When this reaction is observed, if alcohol is treated with any protic acid, alcohol treated with any protic acid, in that case also we will observe this RO bond cleavage. We'll have some more reactions where I will observe, or where we will observe, this RO bond cleavage, like the reactions of alcohol with PCl3, PCl5, SOCl2, SOCl2 with pyridine, and lot of reactions are there which we are going to discuss, where we will observe RO bond cleavage. Okay, even the reactions of alcohols with halic acid, HX, in that particular case I am going to observe RO bond cleavage. So if alcohol is treated with any base, we are going to observe OH bond cleavage. If alcohol is treated with a certain reagent like PCl3, PCl5, SOCl2, SOCl2 pyridine, HX, in all H2SO4, H3PO4, in all such case, we will observe RO bond cleavage. Am I clear, students? So let's discuss these two chemical reactions, or these two types of chemical reactions one by one. First, let's talk about the acid-base reactions of alcohol, where alcohol is acting as an acid and it is having a tendency to release H+. Let's talk about that. Students, whenever alcohol is treated with any alkali metal, this alkali metal acts as a base. Alkali metal acts as a base, and what this alkali metal will do? I will observe this OH bond cleavage treated with sodium. Okay, so what I will observe? I will observe the formation of RO minus as alkoxide ion, and along with this, I will have the formation of hydrogen gas. It's also used as a test for alcohol. If I'm having a bottle, I don't know which type of solution is present. I will simply drop some sodium pellets. If we observe effervescence of hydrogen, it confirms the presence of alcohol. Alcohol treated with alkali metal always releases hydrogen gas. Here I will take half H2. Okay, so this particular reaction indicates the acidic nature of alcohol, and now of this particular reaction will simply depend on the acidic strength of alcohol. Higher the acidic strength of alcohol, better is the extent of this reaction, right? Higher the acidic strength, more will be the tendency to release H plus, and better will be the rate of reaction. Now we have studied this acidic strength of alcohol, right? We have studied, if I talk about aliphatic alcohols, among aliphatic alcohols, methanol is relatively more acidic as compared to other alcohols, right? Like ethanol, propanol, butanol, and so on. Why? Because in case of ethanol, propanol, if I form the conjugate base, that conjugate base will be relatively less stable. So methanol in aliphatic alcohol is going to be more acidic. Even it is more acidic than water, right? So methanol then will have 1 degree, 2 degree, 3 degree. Why 3 degree alcohol is less acidic? The answer is simply form the conjugate, check the stability. In case of 3 degree, the conjugate will be less stable because I am having more plus I groups attached to it, right? Okay. So can I say the rate of reaction is directly proportional to acidic strength of alcohol. More is the acidic strength, better is the rate of reaction. Shall we move ahead? Okay. Students, now let's discuss one more reactions of alcohol where we check the acid-base reaction, and which is all about the acid-base reactions of alcohol. Alcohol acting as an acid. I'm having a substrate ethanol, CH3CH2OH, and it's treated with a base NaOH. Can you tell me the product? The product which you will tell is CH3CH2O negative, CH3CH2O negative, Na positive, that is alkoxide ion, along with OH minus, snatching H plus from alcohol, forming water. Now, between ethanol and water, which one is more acidic? Water. It's a weaker acid. Water is a stronger acid. In which direction the reaction will be shifted? Will a weak acid give a strong acid? No, not in accordance with Li-Thalien's principle. Li-Thalien's principle always say strong acid plus strong base always moves in the direction of weaker acid plus weaker base. So if ethanol is treated with NaOH, the extent of this reaction in the forward direction will be very, very less. It will be maximum shifted in the reverse direction or the backward direction towards reactant side. But if the alcohol is methanol, CH3OH plus NaOH, in that particular case, I will have my product as CH3O negative plus H2O. Now, between methanol and water, methanol is a stronger acid. So strong acid always moves in the direction of weak acid. Now this particular reaction will be shifted in the forward direction. Right, students? I hope you understood this one. So if you are having any aliphatic alcohols and if it's treated with NaOH, and if R is not methyl group, in that particular case the extent of acid-base reaction will be very less. But if the aliphatic alcohol is methanol, in that particular case reaction will shift in the forward direction, and the reason is strong acid always moves in the direction of weaker acid. Strong acid plus strong base gives weak acid plus weak base. Am I clear, students? So shall we move ahead? Let's move ahead. Now, one of the most important chemical reactions of alcohol is esterification reaction. We can say it as one of the most important reactions. You can see the questions coming from this particular subtopic in JEE Mains, NEET, and even in JEE Advanced. This is one of the most favorite topic of JEE Advanced people also. So let's discuss this particular reaction. Esterification or ester formation. We have studied this reaction from class 10th onwards. Carboxylic acid or acetic acid or any carboxylic acid treated with alcohol gives ester plus water. Acid plus alcohol gives ester plus water, right? We have studied this reaction. Now it's time to discuss the mechanism of this reaction. Okay. Student, I'm having RC double bond O, OH. It's treated with R dash OH in the presence of H plus. Now you can say, sir, what this H plus will do? This H plus is used as a catalyst. Used as catalyst. It increases the reactivity of this carbonylic carbon. How? Let's see. I'm having RC double bond O, OH, right? No doubt this carbon is having positive charge, but this positive charge is getting neutralized by the lone pair of this oxygen plus M, right? So electron deficiency will be very less. Now if I treat this with an H plus, what this H plus will do? Oxygen is having lone pair. Whenever you see oxygen having lone pair and you see H plus, do the protonation. Okay. Now you may say, which oxygen will get protonated? Oxygen number 1 or oxygen number 2? Student, here the lone pair is used in resonance. This lone pair is localized. So here the availability of lone pair or electron density is more on oxygen number 2. So can I say oxygen number 2 will undergo protonation? I will have R C double bond O H positive OH. Now this pi bond will shift and I will have formation of R C OH OH and positive. Now I am having a complete positive charge, right? And here on this positively charged carbon, this alcohol will come and will attack. So alcohol is behaving like a nucleophile here. Alcohol is having a nucleophilic behavior in this esterification reaction, right student? So what will happen in the next step? Let's see. I'm having the formation of RC double bond O, OH treated with H plus. I formed RC, OH, OH positive, and on this positively charged I am having ROH. Let's keep it as R dash. Now it will attack lone pair. Lone pair will act as a nucleophile, will attack over here. I will have the formation of R, C, OH, OH, O, positive, H and R, right? Now student, a very important point. Carbon containing 2 OH group. Such a carbon is referred as geminal hydroxyl system. This one, carbon containing 2 halogen, geminal dihalide. Carbon containing 2 OH, geminal hydroxyl. And such a system is highly unstable. Why? Why it is highly unstable? The reason is, I will have a 4-member intramolecular hydrogen bonding, and here IMHB is a destabilizing factor. So whenever you see 2 OH group, simply remove one H2O from here. You will say, sir, always hydrogen bonding is a stabilizing factor. Here why it's a destabilizing factor? Because of IMHB I am having a 4-member cyclic ring formation, right? Because of IMHB I am having a 1, 2, 3, 4-member cyclic ring formation, and the 4-member ring is a highly strained ring, right student? Because of this it is highly unstable and it readily loses 1 mole of water molecule. So I am going to remove this OH and this one. I am going to form one double bond over here. Oxygen having positive charge. will easily undergo deprotonation. Why? Because the electronegative element cannot bear positive charge on it. It will readily undergo deprotonation. I will have the formation of R, C double bond O, O, and this one was R dash. Okay. Now, all the time, you cannot do this. You cannot write the entire mechanism. So now let me give you a shortcut through which you can do this esterification reaction. I'm having a acid CH3 C double bond O, OH. And you are treating it with a alcohol CH3 O18H. In the presence of H plus. This esterification reaction is always a catalyzed reaction. Why? This H plus will increase the reactivity of this carbonylic carbon. Right, student? Now, can you form the product? I am giving you 30 seconds. Please form the product. I hope you have written the product. Student, whenever you are having an acid and one alcohol, you have to do only one thing. Remove hydrogen from alcohol. Remove H from alcohol. Remove OH from acid and simply join these two species. So I will have CH3. I will first write the acid up to the carbonylic carbon. I will remove OH and now I will attach this one CH3O18. So I will have O18 CH3. I hope you understood this one. Remove OH from acid, H from alcohol and combine these two or join these two, right? I hope you understood this one. Please copy it. Students, now you are having certain questions and you need to do these questions. First one, simple. Acetic acid treated with ethanol. What you are going to do? Remove OH from acid, remove H from alcohol and then join these two species. So I will have CH3, C double bond O, O18, CH2, CH3 as my final product. I hope you understood this one. Okay, one or two more questions we have. Can you do these questions? Please attempt it. Really, very important one. I'm having alcohol at the same time here also I'm having a nucleophilic behavior. And it is treated with an acid derivative, not exactly acid. What will happen, student, here? Now, oxygen is also having a lone pair and this nitrogen is also having a lone pair. This oxygen can also behave as a nucleophile and nitrogen can also behave as a nucleophile. Now, between O and N, which will have a better nucleophilic character? Nitrogen. Why? Lesser the electronegativity, higher the donation ability. So, the attack will be on this from nitrogen side. As soon as nitrogen, the lone pair attacks on this carbonylic carbon, this bond will shift over here. I will have the formation of this one first of all. NH positive and it is joined to C, CH3, Cl and O negative. Right, student? And here I am having CH2OH as it is. Now, O negative and leaving group as chlorine. We've studied this reaction, right? O negative will back delocalize, Cl will get departed, nitrogen cannot bear positive charge on it, will easily undergo deprotonation, so it will lose one H plus from here, Cl minus from here. And the product which I am going to get is this one. N C double bond O CH3 CH2OH. So here instead of ester I am getting amide. Now can you do this one? Simple. Very simple, students. Remove H from alcohol, OH from acid, join these two. Remove OH from acid, H from alcohol, join these two. So you will have C double bond O, O18, CH2, C double bond O, O18, CH2. And these two are also connected. So how many member cyclic ring? 1, 2, 3, 4, 5, 6. A 6-member cyclic ring. I hope you understood esterification. Now students, here if I talk about this esterification reaction, the rate of esterification reaction depends on the nucleophilicity of alcohol. Let me write here. Rate of esterification depends on the nucleophilicity of alcohol. Smaller this R group, better is the nucleophilicity, better the rate of esterification reaction. So if you are given ethanol, propanol, butanol, methanol, in which case you are going to have a better rate of esterification? In case of methanol, smaller the size of this R, better is the rate of esterification. So rate of esterification will be much better in CH3OH, then ETOH, right? Then we'll have a 2 degree OH, 3 degree alcohol. The rate of esterification will be very poor, right? Higher the steric crowding, lesser the nucleophilicity, lesser will be the rate of esterification. Now one more thing, this rate of esterification will also depend on the reactivity of this acid or the carbonylic carbon of the acid. So smaller the acid, smaller the alkyl group attached to the carbonylic carbon, R, C double bond O, OH, smaller the size of this R, better is the rate of esterification. So you are having formic acid, ethanoic acid, HCOOH, ethanoic acid, propanoic acid, in which case you will have faster rate of esterification. In case of formic acid, then acetic acid, then propanoic acid. Larger the size of alkyl group, more will be the steric crowding, lesser will be the rate of esterification reaction. Two things. Rate of esterification is important, and one more thing. What will be the product? Remove H from alcohol, OH from acid, join these two. Simple. I hope you understood this esterification reaction, students. So shall we move ahead? Please copy it. Let's move ahead, students. Now it's time to discuss the reactions of alcohol with HX. So here I am going to observe RO bond cleavage. ROH till yet OH bond cleavage was there. Now I will have RO bond cleavage. Students, I am having alcohol ROH. It's treated with an halic acid HX. What this acid will do? It will act as a source of H+. And whenever alcohol is treated with H+, the first step is protonation of alcohol. ROH treated with H+, oxygen having lone pair, simply do the protonation, formation of ROHH positive. Now if this R is 2 degree or 3 degree, better 3 degree or more stable, then remove this, form R plus, and then do the attack of X minus. I hope I am clear, students. If this alkyl group is more bulky and more stable, suppose after the departure of this H2O, I will have the formation of carbocation. If the carbocation formed is more stable, easily remove this H2O, form the carbocation, and then do the attack of X minus. You will have the formation of alkyl halide. So we have formed alcohol from alkyl halide, and now we are going to form alkyl halide from alcohol. Now Student, if I talk about this particular reaction, it will depend on two species, right? First on HX. It will depend on the acidic strength of HX. Now if I compare the acidic strength of HX, I am having HI, HBr, HCl, HF. Relatively a weaker acid. It's very tough to break this HF bond, right? Because of the high electronegativity of fluorine. The bond length is also less, so bond energy will be more here. Here, in case of HI, the bond energy is very less. Lesser the bond energy, easily it can clear, and I will have formation of H+. So if I talk about the reactivity of this particular reaction, it will depend on the acidic strength of HX. HI, more acidic, I will have better rate of reaction with HI. HBr also will work. It will work till HCl, although even this HCl alone won't be able to protonate alcohol. For this, we need some other reagent. We can do the protonation of alcohol more easily with HI and HBr. We can do the protonation of alcohol more easily with HI and HBr. HCl will do, but we need some more specific reagents. I hope I am clear, students. The second thing, once the protonation is done, the next step is the formation of carbocation. More is the stability of carbocation, faster will be the rate of reaction, right? So can I say, in case of allyl, benzyl and 3 degree alkyl halides, will have a resonance stabilized or a highly stable carbocation. In this particular case, if I treat alcohol with HX or with HI, the rate of reaction will be faster. If I am having a allylic halide, if I am having a benzylic halide, if I am having a 3 degree alkyl halide, in all such case, I will have faster rate of reaction. Right, students? If I am having a 1 degree alkyl halide, no. In that case, the carbocation form will be very, very unstable, right? The rate of reaction will be very slow. I hope you understood these things. Please copy it. Students, let us do these two questions in order to understand this concept in a better way. I'm having a monohydric alcohol and it's treated with an acid HI. Source of H+, what it will do? It will do the protonation. So I will have the formation of C, Me, Me, H, and I will have COH, H, positive H and CH3. Right, student? I hope you understood till here. Now, this H2O will depart. I will have a formation of 2 degree carbocation. And now this 2 degree carbocation may undergo further rearrangement. Why? Because if I shift this hydrogen from this particular carbon to this carbon, I will have a formation of 3 degree carbocation, which is more stable as it is containing more number of alpha hydrogen. So I am going to form a 3 degree carbocation. C, Me, Me, positive C, H, H, CH3. And now on this rearranged carbocation, I minus will attack. And I will have the formation of C, Me, Me, I, CH2, CH3. Right, students? So this is my final product. I hope you understood the first one. Now second one, it's really important. Okay. Student, here I am having HI. What this HI will do? It will do the protonation of both the alcohol. So I will have the formation of CH2, CH2, I and I. Now this vicinal iodide system is highly unstable. As soon as it is heated, it readily loses iodine molecule. It undergoes dehalogenation process, removal of both the halogen. Now I will have the formation of alkenes, CH2 doubly bonded CH2. I am having excess of HI. Still I am having HI. Now this HI, what it will do? it will do electrophilic addition reaction here. So this pi bond will break. On one carbon, hydrogen will get attached, and on other carbon, iodine will get attached, and I will have the formation of CH3CH2I as my final product. I hope you understood these two questions. Please copy it. Students, moving ahead with the reactions of alcohol with HX, they are a very important reaction, and this reaction is also used as a test for alcohol. It is used to detect 1 degree alcohol, 2 degree alcohol, and 3 degree alcohol. Highly important reaction. So let's discuss it. And the test name is Lucas test. Okay. Student, if I talk about this particular test, the substrate we take is first, I'm having alcohol, any alcohol, ROH. Then the reagent which we take is anhydrous ZnCl2 along with HCl. Right? I have already told you this HCl cannot easily do the protonation of alcohol. That's why we need one more reagent, and this is anhydrous ZnCl2. What it will do? Will act as a Lewis acid. Okay. Now, how does this reaction occur? Let's first of all try to understand it. I'm having an alcohol ROH. It's treated with anhydrous ZnCl2 along with HCl. First, this alcohol having lone pair, it is nothing but Lewis acid. I will have acid base reaction acting as a alcohol acting as a Lewis base. It will attack on this ZnCl2, and I will have formation of RO positive ZnCl2 negative H. Right? Now this one will act as a very good leaving group. Now Cl minus will come and will attack, and I will have the formation of RCl, and this RCl will give me the turbidity. Student, with the formation of this alkyl chloride, I will have the formation of or the appearance of turbidity. Okay. Now whether I will get instant turbidity after 5 minutes, turbidity on a prolonged duration will depend on this R. Students, this is really important. If I am having a 3 degree alcohol or a resonance stabilized alcohol, in that particular case we will get instant turbidity. If I'm having a benzylic alcohol, if I'm having a allylic alcohol, if I'm having a 3 degree alcohol, in all such cases we will have instant formation of RCl, we will have instant turbidity. If this alcohol is a 2 degree alcohol, then turbidity will appear, formation of RCl will occur, but the turbidity will appear after 5 to 10 minutes. The turbidity will appear after 5 to 10 minutes if I am having a secondary alcohol, and if this secondary alcohol is treated with Lucas reagent. The reagent is anhydrous ZnCl2 plus HCl. Students, if I am having a primary alcohol, in that particular case, turbidity will appear on after infinite time or on prolonged duration. Let me write. Turbidity will appear after prolonged heating. Right? So If it's a 3-degree alcohol, instant turbidity. 2-degree alcohol, turbidity after 5 to 10 minutes. If it's a 1-degree alcohol, in that case, you will have turbidity, but after prolonged duration, after infinite time, you can say. After 10 hours, after 5 hours, on prolonged heating. Am I clear? Now, let's do some questions in order to understand this Lucas test in a better way. Which of the following will respond immediately to Lucas test? Simply, student, if you have to check, or if you have in the question, if it is asked, which of the following alcohol will give immediate turbidity, simply check stability of R positive. Simply check stability of R positive carbocation. If the carbocation formed is a highly stable carbocation, you will have instant turbidity, right? Okay. The carbocation, it's a 2-degree alcohol, so the turbidity will appear, but after 5 to 10 minutes. Secondary alcohol won't give instant turbidity. This one, primary alcohol, no, I won't have instant turbidity, right? The carbocation formed is not that stable. Okay. This one, the carbocation won't get formed at all, right? So I won't get instant turbidity here also. Next one, here I will have the formation of this CH2 positive. Whenever you are having allylic alcohol, benzylic alcohol, or a 3-degree alcohol, instant turbidity. Why? Carbocation formed is a highly stable carbocation, resonance stabilized carbocation. Here, at Bridges position, we cannot form carbocation. I won't get instant turbidity. The same one? Okay. I won't get instant turbidity. If I talk about this one, will I get immediate instant turbidity? The answer is yes. Simply remove OH, put positive charge, check the stability of carbocation. If the R plus, if the carbocation formed after removal of OH is a highly stable carbocation, in that case we will have form instant turbidity, like allylic alcohol, like this one. OH. Will it give instant turbidity? Yes, although it's a primary alcohol, 1-degree alcohol, but this is a allylic alcohol. The alcohol is resonance stabilized. Lot of students gets confused. They will see 1-degree alcohol, so won't give instant turbidity. No, it will give instant turbidity because it is a resonance stabilized carbocation. So simply you have to check stability of R plus, right? Let's move ahead, student. I hope you understood this Lucas test. Moving to the next reaction of alcohol, where once again we will have RO bond cleavages, reaction of alcohol with halogenating reagents. And these halogenating reagents are PX3, PX5, SOCl2, SOCl2 in the presence of pyridine. We will discuss all these halogenating reagents one by one. First, let's talk about the reaction of alcohol with PX3, and this PX3 can be PCl3, PBr3, PI3, even red P plus X2. It's also a source of PX3 only. Okay, the product which we will get is Rx 3 moles of alkyl halide along with H3PO3. Suppose I am having CH3 CH2OH and it's treated with PCl3. What will be the product? The product will be CH3 CH2, replace this OH with chlorine along with H3PO3, right? Okay, now the important point about this particular reaction is this reaction mainly occurs via SN2 pathway, and if this reaction is SN2 pathway, we will observe inversion. So inverted product. The attack of Cl minus. So basically from here we generate Cl minus, and this Cl minus attacks from backside, and this one is departed. Right? I will have the formation of H3PO3 as byproduct. This one is also really important. So I'm having alcohol, 3 moles of alcohol treated with pX3. I will have the formation of 3 moles of alkyl halide. Along with that, I will have the formation of H3PO3. Alcohol with PCl3, alkyl halide plus H3PO3. The product will be inverted one. The reaction is occurring via SN2 pathway. No rearrangement. No rearrangement. Let me write that also. No rearrangement. Okay, shall we move ahead? Please copy it. I'm having OH treated with PCl3. What it will do? Simply chlorination, and OH is on the wedge. Reaction is occurring via SN2 pathway. So I will have the formation of alkyl halide, that is alkyl chloride. But this chlorine will be there on the dash along with H3PO3. I will have 3 moles. 3 moles of alcohol is treated. This one is also important, the moles. They may ask. Okay. The second one, PCl5. Great. Student, here also the reaction will occur via SN2 pathway only. I will have halogenation reaction. Alcohol will get removed, replaced by halogen. I will have the formation of alkyl halide, right? But here the byproduct formed is P double bond O, Cl, Cl, Cl. POCl3 is the byproduct, and the main product is alkyl halide. Okay, so let me write the chair form, and if it's there on equatorial, I'll have chlorine on the axial position. Am I clear, student? Inversion. The reaction is once again occurring via SN2 pathway. This is important. The product is going to be a inverted one. Inverted. We'll have Walden inversion once again here also. I hope you understood. PCl3, formation of H3PO3 along with alkyl halide. PCl5, formation of alkyl halide via SN2 pathway along with POCl3 as a byproduct. Here basically this PCl5 splits as PCl4 plus, PCl6 minus, and then the reaction occurs. But the mechanism is not really important for JEE mains and NEET. Okay. Students, I am having alcohol treated with red P plus I2. What this red P plus I2 will do? Once again, halogenation. Both OH will get replaced by CH2I, vicinal diiodide system. Unstable, may easily undergo dehalogenation and have the formation of alkene. If I talk about this red P plus HI, excellent reducing agent. Excellent. Let me write it in a better way. Excellent reducing agent, or we can say it as king of reducing agent or father of reducing agent. It say I am the father of reducing agent. What it will do? Will reduce alcohol to alkene. So here I will have the formation of CH3. In this case I may have the formation of alkene also. So here I have kept the vicinal diiodide. Highly unstable, will easily undergo dehalogenation, remove both the halogen, and I will have the formation of CH2. Right? So in the first case I am going to get alkene, whereas in the second case I am going to get alkane. I hope you are crystal clear with this concept. Shall we move ahead? Let's move ahead. Now moving ahead, let's discuss one of the most important reaction, and that is the reaction of alcohol with SOCl2. This reaction occurs via SNI pathway, intramolecular nucleophilic substitution reaction, also referred as Darjan's process. Darjan's process. How does this reaction occur? Let me explain you. I'm having alcohol, right? I'm having S double bond O, Cl, Cl, sulfur from third period having a vacant 3d orbital will act as a Lewis acid. Oxygen having lone pair will act as a Lewis base. It will do the nucleophilic attack on the sulfur. As soon as it attacks, I will have the formation of R, O, H positive, S, O negative, Cl and Cl. Oxygen cannot bear positive charge on it. Will readily undergo deprotonation. This O negative will also undergo back delocalization and this chlorine will get departed. I will have the formation of R, O, S, double bond O, Cl. Now this is formed as an intermediate and it will undergo rearrangement. How? Let's see. Students, I am having R, O, S, double bond O, Cl. What happened? Basically, student, this chlorine will attack on this alkyl. Oxygen lone pair will undergo delocalization. So as soon as it undergo delocalization, oxygen will have positive charge. So this bond will cleave. Simultaneously, this bond will also cleave because chlorine will form bond with alkyl group. So I will have removal of SO2. At the same time, I will have the formation of RCl. So the product which we'll get is RCl plus SO2. Now, stereo-wise here, retention occurs. Means if alcohol was there on the wedge, chlorine will be there on the wedge only. If alcohol is on dash, chlorine will be there on dash only. Please copy it. So this reaction is occurring via 4-member cyclic transition state. That's why it's a SNI reaction, intramolecular nucleophilic substitution reaction. Please copy it. Okay. So I'm having alcohol treated with SOCl2. What will be the product? Alkyl halide, chlorination. Simply remove OH with Cl. Retention of configuration. This stereo is also important. So if alcohol is on wedge, chlorine is going to be on wedge only. Right. Next one. SOCl2 along with pyridine. Now this reaction won't occur via SNI pathway. Here, if I am having SOCl2, this is really important. SOCl2 in the presence of pyridine and absence of pyridine. If absence of pyridine, I will have SNI, retention. Presence of pyridine, reaction will occur via SN2 pathway. So I will have inverted product. Alcohol on the wedge, chlorine will be on the dash part. This is important. Stereo wise, SOCl2 in the presence of pyridine, written inversion. SOCl2 in the absence of pyridine, retention. Please complete. Student, I am having one more reaction. I am having CH2, CH, CH2OH, perfect, and it's treated with SOCl2. Okay, and in this case, you need to tell me the product. Whether the reaction is occurring in the presence of pyridine or absence of pyridine. Absence of pyridine. So the reaction will occur via SNI pathway. And this question is really important. Lot of students will commit mistake. See how this reaction will occur. I am having CH2, 14, isotopic part is taken. Doubly bonded, CH, CH2, O, H, lone pair, treated with S, double bond O, Cl, Cl. Right? I will simply remove H from here, Cl from here, and I will write the intermediate. The intermediate formed is CH2 14 doubly bond CH, CH2 O S double bond O Cl. Okay. Now let me write it in a better way. I am having CH2 14 doubly bonded C, right student, H, CH2, I am having O, perfect, then S, double bond O, Cl. Okay. In that particular case, when I was having an aliphatic alcohol, ROH, treated with SOCl2, I was having a 4-member cyclic transition state. Here, let's see. 1, 2, 3, 4, 5, and 6. What will happen? This chlorine will attack here. As soon as it attacks over here, this pi bond will shift here. Right? As soon as this pi bond shifts here, this bond will cleave. Oxygen will delocalize. The lone pair of oxygen will delocalize. I will have removal of SO2. So, can you tell me the product? The product formed is chlorine is getting attached to isotopic carbon C14, that is chlorine getting attached here, and here it's having 2 hydrogen, right? Now double bond shifting to the next carbon, so I will have now single bond, 3 sigma bonds and 1 sigma bond. Now between these 2 carbon I will have double bond CH2, right? And now this SO2 is getting clear. I hope you understood this particular question. Really important question. Now student, this particular question won't appear in NEET, may appear in JEE mains, and may definitely appear in JEE advanced. Okay. So shall we move ahead? Please see, please have a look, try to understand it. If you face any difficulty in this particular question, please mention in the comment box. I will readily, or I will be very happy to answer it. Now it's time to talk about dehydration of alcohols. This one we have discussed in alkene also. In the GMP of alkene, alcohol on dehydration generates alkene, right? I'm having alcohol COH. If it's treated with any dehydrating reagent will have the formation of alkene. Now in certain case we'll have the formation of carbocation. Now you will say, when I will have the formation of carbocation? Student, if alcohol is treated with protic acids, ROH, treated with any of the protic acid like H2SO4, H3PO4, in that particular case, I will have the formation of R+. This R+ will undergo further rearrangement. And then I will form the most stable carbocation. And from here, I will form ZF alkene. If I am having dehydrating reagents like POCl3, Al2O3, in that case, elimination will occur via E2 pathway. Here the elimination is occurring via which pathway? E1 pathway. First step, you need to do the protonation. Acid, source of H+. This H+ will protonate alcohol. I will have the formation of carbocation. Rearrangement, most stable carbocation. Remove beta hydrogen from the alkene, or remove beta hydrogen from that carbon which is more substituted, so that you will get a more substituted alkene, that is ZF alkene. Okay. Already we have studied about dehydration of alcohol a lot in hydrocarbon. Still, let's do one question in order to understand this dehydration of alcohol in a better way. You are having a question, alcohol treated with conc H2SO4 with heat. Please do this question. Okay, shall we start? Yeah, I'm having alcohol. This alcohol is treated with H plus. I will have the protonation, right? Okay, removal, formation of carbocation. Whenever alcohol is treated with any protic acid, that acid which is having H plus, always I'm going to form a carbocation. Now this carbocation will undergo further rearrangement. Why? I'm having a 5-member cyclic ring. Just outside the cyclic ring, I'm having a positive charge. So this ring will undergo ring expansion. How? Let's see. Can I shift this alkyl group to here on this carbon? Now if I count it, I will have 1, 2, 3, 4, 5, 6-member cyclic ring, right? So this 2,6 bond will cleave and it will join to 1,6. It will form a 1,6 bond, right? Let's form it. Student, okay. Now I'm having 2,3 bond, 3,4 bond. This is 2,3, 3,4, 4,5, 5,6, and now this 5,6 will get connected to 1,2. Let me connect it via different color. 1,2, right? Okay. Obviously, this 1,2 bond is, this 2,6 bond is cleaving and it's getting connected to 1,6. So 2 is having a deficiency of 1 bond. So can I say here I will have a positive charge? Now 1, 2, 3, 4, 5, 6, right? So I'm having a 6-member cyclic ring. To this cyclic ring, one more cyclic ring is attached, right? Like this. How many member? 1, and let's keep it like this, right, student? And here this one, 1, 2, 3, 4, 5, 6, 1,6 bonds getting connected. Positive charge. 1 hydrogen is here. Can I remove this hydrogen and can I form the most stable alkene? Definitely yes. Remove this hydrogen and form the alkene here. So this is my final product, students. I hope you understood this one. This one. And now here I'm having a product like this. This is my final product. Is it clear, everyone? Please copy it. Students, now it's time to discuss one of the most important application of dehydration of alcohol, and this reaction is referred as pinacol-pinacolone rearrangement. Pinacol, it's nothing but vicinal diol system. Vicinal diol. And this vicinal diol, whenever treated with a protic acid like H2SO4, H3PO4, undergo rearrangement and forms a carbonyl compound. And this carbonyl compound is pinacolone. I hope you understood this. Now it's time to take one example and we will try to understand the mechanism through that example itself. Okay. Student, let's take one example. CH3. CH3 OH. Here I am having C, H, Me and OH. Is it a vicinal diol system? The answer is definitely yes. Now it's treated with a protic acid H2SO4. Step 1. Attack of H plus on that alcohol which forms a relatively more stable carbocation. Attack of H plus, because this H2SO4 is a source of H plus, and this H plus will attack on that alcohol which forms a relatively more stable carbocation. Now, so it will attack on which carbon? Carbon 1 or carbon 2? If I attack this H plus on this carbon 2, I will have a more stable carbocation, right? Okay, so I will attack this H plus on this alcohol. I will have the formation of CH3, CH3, OH, H positive, COH, H, Me. Now students, what will happen? This H2O is a very good living group. Departure, formation of a more stable carbocation, C, Me, C, H, Me, OH. Okay, now a very interesting story here. No doubt this carbocation is more stable, but we have studied a carbocation stabilized by back bonding is much more stable. If anyhow, if I shift this positive charge to this carbon, can I say I will have a carbocation stabilized by back bonding? Right? Because oxygen is having lone pair. So if this positive charge comes to carbon number 1, I will have a formation of carbocation, and that carbocation is getting stabilized by back bonding. So now here, how will I shift this carbocation here? By migration of one alkyl group. So can I say one of the group has to migrate from here, then only I will have the formation of C positive here. So from let's suppose it was having carbon 1 and carbon 2, I have to form positive charge on carbon 1. So I have to cleave one of the bond from carbon 1 to form a positive charge, right? Okay. Now between methyl and hydrogen, which one will have a better migration ability? Student, first of all, let me write the migration ability. H, then pH, then 3 degree, then 2 degree, then 1 degree methyl. Okay. If I talk about pH also, if it's a substituted pH like OMe and NO2, which pH will have, which ring will have more nucleophilic behavior? That ring will have more nucleophilic behavior which is connected to a plus N group, right? So this one will have a better migration ability as compared to this one, because this one will destabilize, right? Okay. So what will happen here? Now this hydrogen will migrate from carbon 1 to carbon 2. I will have the formation of C. Hydrogen had shifted here. I'm having one Me, right student? Okay, one more Me was there. Now I will have positive charge here since this carbon has lost hydrogen. OH is there and one Me is there. Now can I say I'm having a carbocation and this carbocation is connected to OH. This lone pair will undergo delocalization. I will have the formation of CH, Me, C double bond OH, Me. Oxygen having positive charge will readily undergo deprotonation. I will have the formation of CH, Me, C double bond O, Me. Finally, the product formed is a ketone. Now you will say how to remember it. Student, 2 steps only. Simply form the attack of H plus. Step 1, attack of H plus. Form a more stable carbocation. Simply attack H plus on that alcohol which is forming a more stable carbocation. And step 2, migration of one of the alkyl group to form a carbocation stabilized by back bonding. Now you have the migration ability order. H, pH 3 degree, 2 degree, 1 degree. Do the migration according to this migration ability order, okay, or migration aptitude order, and then form the carbonyl. Am I clear? Step 1, formation of a more stable carbocation. Step 2, migration of alkyl group to form a carbocation that is stabilized by back bonding. Form the carbonyl compound. Simple. Let's practice some question. I am having here attack of H plus to which alcohol, which forms a more stable carbocation. If I attack on this alcohol, I will have a resonance stabilized carbocation. So simply this H plus will attack here. I will remove it. I will have the formation of C, Me, Me, OH, C, positive, pH, Me. Now, step 2, rearrangement. One of the methyl will migrate because only methyl group is there. So that I will form the carbocation on second carbon, which is stabilized by back bonding. So now I will form the carbocation here. Methyl group has migrated, OH. Now I am having C, pH, Me. One of the methyl has migrated and one methyl was present from the beginning itself. Back delocalization, remove this H. The product formed is Me, C double bond O, C, pH, Me and Me. Right? Form the more stable carbocation, migrate one of the group, form the carbonyl on the other carbon. Is it clear? Okay, next one. Here, this question is really interesting. Vicinal diol treated with H2SO4. Source of H plus, protonation of alcohol. Which alcohol will get protonated? That alcohol will get protonated, which forms more stable carbocation. This one. 2 ring activating group is there. So I am going to form carbocation here. Right, student? In one step I will do now. I will form the carbocation here. Remove H2O. Now, migration. Which ring will migrate? So that I can form carbocation on this carbon. pH and OMe. That ring will migrate which is having a, or which is more activated, which is having higher electron density. OMe will migrate here. I will form the positive charge here. So I will have C, pH, positive charge, OH, C, OMe. Already one it was there and one OMe has migrated to this carbon. So 2 pH OMe and 1 pH OH, right? And now simply form the double bond here. So the product which I am going to write is pH, C double bond O, C, pH with OMe, pH with OMe and pH with OH. Right, student? I hope you understood this one. Students, now let's talk about the oxidation reactions of alcohol. Let us first of all talk about oxidation of primary alcohol. I am having primary alcohol. The general formula is RCH2OH. And now it's treated with an oxidizing agent. We are having 2 different types of oxidizing agent. One mild oxidizer, one strong oxidizer. Let's first of all talk about strong oxidizing agent. Strong oxidizing agent. Primary alcohol on reaction with strong oxidizing agent. First we get RC double bond OH, aldehyde as an intermediate, but it's further oxidized to RC double bond OOH. So primary alcohol on reaction with a strong oxidizing agent always generates carboxylic acid. Now you can tell, sir, what are the strong oxidizing agents? I am giving you the list. Strong oxidizing agents are OAR first. You can have alkaline KMnO4. You can have acidified K2Cr2O7 H plus. You can have even HNO3 also. Students, basically these 3 reagents are treated as a strong oxidizing agent. Whenever you see primary alcohol and these are the oxidizing reagents, the final product is always an acid. Primary alcohol on reactions with these reagents, any of these reagents will always generate carboxylic acid. If I am having a mild oxidizer, same primary alcohol now treated with mild oxidizer. Mild oxidizer. The final product is going to be aldehyde. Primary alcohol on treatment with mild oxidizer always generates aldehyde, whereas primary alcohol on treatment with a strong oxidizer always generates carboxylic acid, because the aldehyde part is also getting oxidized. Now you may say, so why the aldehydic part is also getting oxidized? Yes, because it is having one replaceable hydrogen. This hydrogen is getting replaced by OH group. Am I clear, students? Now, primary alcohol, strong oxidizer, acid, mild oxidizer, aldehyde. Now you may ask, sir, what are the different mild oxidizers? Now I am giving you a list of mild oxidizer. If you take any of these mild oxidizer and if you treat it with primary alcohol, you are going to get aldehyde. Now let's have a look at the lists of mild oxidizer. First, the most important, PCC, pyridinium chlorochromate. Pyridinium plus CrO3 plus HCl. Basically, these three reagents combine and form PCC. Sometimes you will directly see primary alcohol and they will give you PCC. They won't write this molecular formula or structural formula. They will simply write PCC. This PCC is a mild oxidizer. Either it can be written in this form or they can simply write PCC. Both of them represent the same thing. It's a mild oxidizer. Next one, Collins reagent. This is also important. Pyridinium plus CrO3 plus CH2Cl2. This is Collins reagent. Acts as a mild oxidizer. So if I am having a primary alcohol and if I react this primary alcohol with Collins reagent, student, I am going to get aldehyde. PCC, Collins reagent. Then we have TSCl, tosyl chloride, DMSO as a solvent, and NaHCO3. This one also acts as a mild oxidizer. Then CrO3 plus CH2Cl2 acts as a mild oxidizer. MBS, M-bromosuccinamide, acts as a mild oxidizer. Then we have X2 in the presence of OH minus. We have to study this reaction, haloform reaction. Basically, it's also oxidation reaction only. So X2 in the presence of OH minus also oxidizes a primary alcohol to aldehyde. Now, first the primary alcohol is converted to aldehyde and then it may further get converted. Now, the last one, H2CrO3 in the presence of acetone. This one also acts as a mild oxidizer. So I have given you a certain list of mild oxidizer. You need to remember PCC, that PDC, then we have Collins reagent. We have one more important reagent, that is CrO3 plus H2SO4. That's basically a strong oxidizer. If you are having a primary alcohol and if you treat a primary alcohol with CrO3 plus H2SO4, you are going to get acid. Okay. Now student, let's talk about the oxidation of secondary alcohol. Secondary alcohol having a general formula RCHOH R-. Whether you treat secondary alcohol with a strong oxidizer, or you take a mild oxidizer, you take either a strong oxidizer or a mild oxidizer. In both the case, your final product is going to be ketone only. So the final product will be RC double bond O R dash, ketone. This ketone does not have any replaceable hydrogen, so it will not get further oxidized. Either you take the strong oxidizing agent like KMnO4, K2Cr2O7, or you take a mild oxidizer like PCC, Collins reagent, TSCl plus DMSO. Any of these, you are always going to get ketone. Am I clear, students? Okay. Students, we have one more oxidizing reagent, and that is copper. Basically, if I pass the vapors of alcohol On copper, primary alcohol gets converted to aldehyde, secondary alcohol gets converted to ketone, and tertiary alcohol gets converted to ZF alkene. Let me write that. Oxidation with copper. Now, I'm having a primary alcohol RCH2OH, and if I treat this primary alcohol with copper at 523 Kelvin temperature, the product which I am going to get is RC double bond OH. Next one, I'm having secondary alcohol. The same reagent, copper, at 523 Kelvin, I am going to get RC double bond OR dash. Now, I'm having a 3-degree alcohol, RC R dash R double dash OH. Is it a 3-degree? Definitely yes. And now it's treated with copper 523. Students, in general, 3-degree alcohol does not undergo oxidation. You may say, why? It does not have any replaceable hydrogen which can get replaced by OH, right? This is the reason a 3-degree alcohol does not undergo oxidation. Now I am having a 3-degree alcohol treated with copper at 523 Kelvin. Can you tell me the product? Student, here the product form is alkene. And which type of alkene will you form? ZF alkene. ZF alkene. Am I clear? The alkene formed is ZF alkene. Please copy this one also. I hope you have copied it. So shall we move ahead? Let's move ahead. Oxidation reactions, resistance of tertiary alcohols to oxidation. Yes, if I am having a tertiary alcohol RC R dash R double dash treated with a strong oxidizer or a mild oxidizer, in both the case, no reaction. You may say, why? Already I have told you there is no replaceable hydrogen H, right? So a 3-degree alcohol in general won't undergo oxidation. Either you take alkaline KMnO4, acidified Na2Cr2O7, K2Cr2O7, or you take any mild oxidizer. In all cases, it is not going to get oxidized, student. I hope I am crystal clear, students. So please copy it. Students, now we have a selective oxidizer, and this selective oxidizer is MnO2. It's also a mild oxidizer, but it is able to oxidize certain species only. It mainly oxidizes benzylic and allylic alcohol only. It mainly oxidizes benzylic and allylic, okay, alcohols only. So I am having a benzylic carbon. This carbon is benzylic carbon, right? And OH connected to this carbon, OH is basically, now I am having a benzylic alcohol. Now this benzylic alcohol is treated with MnO2. Will it be able to oxidize this? Definitely yes. MnO2 only touches benzylic alcohol and allylic alcohol. It is not going to touch a simple primary alcohol, secondary alcohol. Only benzylic and allylic alcohol. So here the product is going to be C double bond OH. Now, if I talk about this OH, is it connected to allylic carbon? Yes. So is the alcohol allylic alcohol? Definitely yes. Will it oxidize this one? Definitely yes. The product is going to be, right? I hope you understood this one also. MnO2, a selective oxidizer, oxidizes only benzylic alcohol and allylic alcohol, right? Please copy it. Students, so now we are done with the chemical reactions of alcohol. You may say, sir, one more reaction is there, acetal, hemiacetal, ketal. But student, that reaction we are going to study in carbonyl compounds, because there we have to study nucleophilic addition reaction. Okay, so we'll study that particular reaction in carbonyl compounds. Now it's time to discuss about ether, and let's start our discussion of ether with GMP part itself, general method of preparation of ether. Now student, the first one and the most important GMP of ether is Williamson synthesis of ether, right? Okay, let's talk about it. Students, basically in Williamson synthesis of ether, what we take? First we take one alcohol, ROH. Now this alcohol is treated with a strong base NaOH. And you see, I will have acid-base reaction and I will have the formation of RO minus. Now this RO minus can act as nucleophile as well as base. If it does not find acidic hydrogen, or then it will act as a nucleophile. If it is having an acidic hydrogen, then it will act as base. Okay, so it can do substitution as well as elimination. Now this RO minus is treated with alkyl halide R-X. Okay, suppose if this alkyl halide is 1 degree or 2 degree, then in that case Nu minus will promote the nucleophile. RO minus will attack here via SN2 pathway from the back side, and I will have the formation of my desired product as ROR dash, right? So here substitution reaction is occurring, and this reaction is occurring via SN2 pathway. Why SN2 pathway? 1 degree or 2 degree alkyl halide and a strong nucleophile. Now the second story, if this alkyl halide is 3 degree alkyl halide, in that case RO minus will act as a base, because this RO minus is having a basic character as well as nucleophilic character. If the alkyl halide is 1 degree or 2 degree, in that case this RO minus will act as a nucleophile and SN2 pathway will dominate. But if this alkyl halide R-X is a 3 degree alkyl halide, in that particular case reaction will occur via E2 pathway mainly, and I will have alkene as the major product. So student, there is a limitation for this Williamson synthesis of ether. The limitation is the alkyl halide taken has to be R-X, must be a 1 degree or maximum 2 degree alkyl halide. If it's a 3 degree alkyl halide, we will not get ether, instead we will get alkene. So the alkyl halide taken in Williamson synthesis of ether has to be 1 degree or 2 degree alkyl halide. I hope I am crystal clear with this Williamson synthesis of ether. R-O minus will attack here, X will depart, I will have the formation of ether. Please copy it. Let's do 1 or 2 questions in order to understand this Williamson synthesis in a better way. Okay. Student, I am having alcohol CH3OH. Definitely it is going to react with NaOH and the product formed is CH3O minus. Can act as a nucleophile as well as base. Now, I am having 1 degree alkyl halide. In that case, the reaction will occur via SN2 pathway. It will do back attack, right? And then this Cl will get departed. my final product form will be CH3CH2OCH3, methoxyethane, right? Methyl ethyl ether as the common name and IUPAC name methoxyethane. Let's move to the second part. Student, here I am having CH3CH2OH treated with OH minus. The product form will be CH3CH2O negative. Now it's treated with a 3-degree alkyl halide. 3-degree alkyl halide won't undergo substitution reaction via SN2 pathway. Nucleophile is strong, so we won't have even SN1 also. So the only one pathway is there, and the reaction will occur via E2 pathway, elimination. So here this one will act as a base. Why it is acting as a base? Because the alkyl halide given is a 3-degree alkyl halide, and in this particular case, if I am having a 3-degree alkyl halide treated with a base, the product form is going to be alkene, C doubly bonded CH2 CH3 CH3. Right, students? Please copy it. Now, student, now let's discuss one more method of preparation of ether, and in this method we are going to do dehydration of alcohol. Now you may say, sir, alcohol on dehydration will generate alkene. This is what we have studied in hydrocarbon also and even in alcohol also. But now you are saying alcohol on dehydration is generating ether. Yes, you heard it right. Alcohol on dehydration may even generate ether. Now, this reaction will depend on temperature. Student, we have studied this elimination reaction is an endothermic reaction, right? And endothermic reactions are supported at high temperature. At high temperature, alcohol on dehydration will generate alkene, and if the temperature is low, near about 140 degrees centigrade, and in that particular case, if I take this alcohol and if I react it with H2SO4 at low temperature, I will have the formation of ether. Let's try to understand how does this reaction occur. Student, I am having an alcohol ROH. It's treated with H2SO4. What is the function of H2SO4? Release H plus. This alcohol will get protonated. I will have formation of ROH positive, right? Now students, if this R is a 3-degree, then this one can easily depart because the carbocation form will be a relatively more stable carbocation. In that particular case, I will have the formation of R positive, provided this R is a 3-degree, right? Or resonance stabilized. Now this R positive is going to react with 1 more mole of alcohol, right? And here I will have the formation of ROHR. Oxygen has donated its lone pair. It will get a positive charge. Oxygen cannot pair positive charge, will readily undergo deprotonation. I will have the formation of ROR, right? This is how ether is prepared by dehydration of alcohol. But the condition is the temperature has to be low. The temperature has to be low. If the temperature is relatively high, in that particular case, we will have Sergev alkene as the major product. If temperature is low, below 140 degrees centigrade, below 150 degrees centigrade, in that particular case, my major product is going to be ether. So, at low temperature, substitution reaction. At high temperature, at low temperature, substitution reaction is dominating. Substitution reaction. And high temperature, elimination reaction is dominating, right? Elimination. I hope you understood this one. Ethers may be prepared from alcohol in acidic medium. Generally, accepted mechanism for primary alcohol is SN2. Yeah, because we cannot form carbocation, right? And if The alkyl is a 3-degree alkyl, then the reaction will occur via SN1 pathway, because in this case I will form R positive, right students? So I hope you understood dehydration of alcohol to generate ether. Lower temperature ether, higher temperature alkene. From alkyl halide, student, if we take alkyl halide and if I treat it with dry Ag2O, the product which I am going to get is ether. So now alkyl halide with moist Ag2O will form alcohol. Alkyl halide with dry Ag2O will form ether. Simple. There is no such mechanism. Simple. Alkyl halide on reaction with dry Ag2O will form ether. Alkyl halide on reaction with moist Ag2O will form alcohol. Moist Ag2O is a source of OH minus. Right? Here I am taking dry Ag2O to form ether. Am I clear? Shall we move ahead? Let's move ahead. It's moving to the next method of preparation of ether that we have on the screen, and this is referred as Oxymercuration-demercuration. Same story, just instead of taking water, right now I am going to take alcohol. So alcohol will act as a nucleophile here. Perfect. Let's see this reaction. Let us assume I am having an alkene like this. Okay, this is the alkene. Now it's treated with HgOAc whole twice along with ROH. Right? So can I say the first step is going to be alkoxymercuration, where I will have the addition of HgOAc and alcohol, and the addition will be anti-addition. Right. So I will have C HgOAc getting added over here, C, and this alcohol getting added to the second carbon. Here the nucleophilic part is RO, so OR will get added here. And now the addition is anti-addition. I hope you remember this one. The next step is demercuration step. Now it is treated with NaBH4. I will have the cleavage of this CHG bond. I will have the formation of CHCOR. Right, student? So basically alkene is getting converted to ether through this alkoxymercuration-demercuration. Right? Let us move ahead. Reactions of alcohol with diazomethane. Can you tell me the general formula of diazomethane? It's nothing but CH2N2. Okay. Let's write the structure of CH2N2. CH, doubly bonded N, positive, negative. This is nothing but diazomethane. Can we do resonance here? Definitely yes. Okay. So this one will delocalize and then this one will delocalize here, and here I will have CH2N triple bond N positive. Right? This is also diazomethane. Now it's treated with alcohol, ROH, treated with CH2 minus N triple bond N positive. Student, can you say this CH2O negative, CH2 negative may act as a base if it finds any acidic hydrogen? And yes, the hydrogen connected to alcohol or oxygen is the acidic hydrogen. This hydrogen connected to oxygen is the acidic hydrogen. So what this CH2 minus will do? It will snatch this acidic hydrogen, and I will have the formation of R O negative plus CH3N triple bond N positive. Right? Now this RO negative will act as a nucleophile, and what it will do? It will do back attack here, and this will get departed. So here the reaction is occurring via SN2 pathway. Finally, I will have the formation of RO CH3 ether. Right, student? So alcohol on treatment with diazomethane will generate ether. I hope you understood this reaction. Please do copy it. Shall we move ahead? Let's move ahead. Friends, now it's time to discuss the chemical reactions of ether. The first reaction that we are going to discuss is the reaction of ether with halic acid HX. Okay, I'm having a halic acid HX. Generally, the acid which we take is either HI or HBr. We don't take HF or HCl because it's very tough to protonate ether using HF or HCl. Let's study about this reaction. I'm having a ether ROR dash. Now it's treated with an acid HX. What this HX will do? It will act as a source of H plus. What this H plus will do? This H plus will protonate ether. So I will have the protonation of ether. Right now, the nucleophilic role will come into picture. Right now, this nucleophile X minus will attack on less substituted carbon. Let us suppose if R dash is less substituted, it will attack over here, and then this one will get departed as ROH. Plus, I will have the formation of R dash X. So, ether on reaction with HX generates alcohol as well as alkyl halide. I hope you understood this one. Now we are going to do the applications of this reaction of ether with very important acid, that is HI. And this particular concept is really important. So we'll do it in a detailed way. Student, I am having a ether ROR dash. Okay. If it's treated with conc HI, the first step is the protonation step, right? So in the first step, what I will have, ROR dash H plus, oxygen will get the positive charge. Obviously the bond has to cleave. Now the nucleophile will come into picture. Now this I minus will attack on less substituted carbon, and the reaction will occur via SN2 pathway. Let us suppose this one is less substituted. So I minus will attack here. As soon as it attacks here, this bond will cleave. So I will have the formation of ROH plus R dash I. Now this reaction is occurring via SN2 pathway. Now you may say, sir, will the reaction always occur via SN2 pathway? I will say no. If both R and R dash, if they are 1 degree or 2 degree, or 1 degree or 2 degree, then the reaction will occur via SN2 pathway. If any one of them is a 3 degree, then the reaction will occur via, if R or R dash, anyone 3 degree, in that case reaction will occur via SN1 pathway. How will the reaction occur via SN1 pathway? Suppose if R dash is 3 degree, then I will have complete cleavage of this bond. I will have the formation of R dash carbocation, and now on this R dash carbocation, I minus will attack. Right, student? I hope you understood this one. Okay, let's try to understand it. Student, let us suppose I am having CH3 OCH2 CH3. Right? And now if it's treated with a acid HI. First step, protonation. So I will have CH3 OH positive CH2 CH3. Both R and R dash are 1 degree or 2 degree. It's also 1 degree and 1 degree. So the reaction is going to occur via SN2 pathway. Now here this I minus will come into picture, and where this I minus will attack? To the less substituted carbon, right? Can I say this one is less bulky? So this I minus will attack here from the back side, and as soon as it attacks, this bond will cleave. So I will have the formation of CH3I plus CH3CH2OH, right? Okay. One more case. I am having CH3CH3 CH3 O CH2 CH3, and now it's treated with conc HI. First step, protonation. I will do the protonation. Now OH positive CH2 CH3, and here I will have C, C, C and C. Now student, will the reaction occur via SN2 pathway? The answer is no, big no. Here the reaction will occur via SN1 pathway. Now how the reaction will occur? Let's try to understand. Here first this bond will cleave. It will act as a leaving group, will depart. So I will have the formation of C, 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 C positive plus CH3 CH2OH, and now on this carbocation I minus will attack. I will have the formation of, right. So if R and R dash 1 degree or 2 degree SN2 pathway, in that case I minus will attack on less substituted carbon, less bulky alkyl group. If R and R dash any one of them is 3 degree, then I minus will attack on more substituted carbon, more bulky carbon, formation of carbocation. Am I clear? Please do copy it. Friends, now let's discuss one more chemical reactions of ether, and here we are going to discuss the reaction of ether with dilute acid, even concentrated acid, or even we can say acidified water. Let's discuss this reaction. First, I am having an ether R2O. It's treated with H2SO4. This H2SO4 is a source of H+. First step is the protonation of ether. I will have the formation of RORH positive, right? Now, attack of water. Attack of water will occur. Since here it's a symmetrical alkyl, it will attack on any one of the carbon. Here let's suppose if it's attacking, it will act as a leaving group. So I will have the formation of ROH along with ROH. But let us try to understand this reaction in a better way through example itself. Students, I am having PHOCH3. It's treated with dilute H2SO4. What this dilute H2SO4 will do? It will do the protonation, right? So in the first step, I will have the formation of PHOH positive CH3. Now, what attack of water will come into picture? Right, student? H2O. Where it will attack? Will it attack on this phenyl? If it attacks on phenyl, then this bond has to cleave, but I cannot cleave this PHO bond, right? It is having somewhat double bond character. Can we cleave this CH3O bond more easily? Definitely yes. So this water molecule will attack over here. As soon as it attacks over here, it will act as a leaving group. I will have the formation of PHOH, that is phenol plus CH3OH, right? Next one, I'm having CH3O18ET, and it's treated with dilute acid or acidified water, meaning it's same. Let me take S3O plus. What will happen now? First step, protonation of ether. I will have CH3O18H plus. So I will have positive charge over here, and then ET. Now attack of water. What do you say? Where it should attack? On methyl or ethyl? This attack of water will depend on leaving propensity. Let us suppose if this water attacks on methyl, then this one has to depart. ETO18H has to depart. If this water attacks on ethyl, then this MEOH has to depart. This one will act as a leaving group. It can act as a better leaving group, right? So can I say water molecule is going to attack on ethyl part? Here in this particular case, simply check leaving propensity. Here the leaving ability of Me, that is methyl O18H, is much better as compared to ethyl O18H. So water molecule will attack on ethyl part. I will have the formation of CH3O18H plus ETOH. Right, students? I hope you understood this one. Please comment. Students, we have one more reaction. Here also I am having ether, and this ether is treated with acidified water. What will happen? Can I say I will have the formation of, right, protonation of both the oxygen, O positive H. Obviously this bond has to cleave, right, and this bond will also cleave. So I will have the formation of, right student, OH, OH, and here if this bond is cleaving, one time water will attack, I will have the formation of OH. If this bond is cleaving, one more water molecule will attack. So on this carbon, I will have two OH molecule, right? And if I am having a structure like this, geminal hydroxyl system, I have already told you it readily undergo dehydration and forms aldehyde. So here I will have the formation of, simply remove H2O from here, and I will form, what will be my final product? OH, doubly bond O, H, and now I will have formation of OH. This is the final desired product. I hope you understood this one also. Please copy it. Students, now let's discuss the third most important compound of this particular chapter, and that is phenol. So now we have moved to the third compound, phenols. If we look at the structure, it is having structure like this, benzene ring, and it is directly connected to OH. So the functional group OH here is directly connected to pH, aromatic alcohol, right? Okay. Student, if I talk about the acidic strength, phenol is always a better acid as compared to all other aliphatic alcohol. Even it is having a better acidic strength as compared to methanol, right? Simple, we have studied all these things in GSC chapter itself. If I talk about the stability of the conjugate, here I am having phenoxide ion which is stabilized by resonance. So phenol or aromatic alcohols are always a better acids as compared to aliphatic alcohol. Now it's time to discuss the general method of preparation of phenol. Okay, so the first one, we have studied aryl halides or haloarenes, right? And there we have studied, if I am having a haloarenes and if it's treated with NaOH, this NaOH is a source of OH minus. This OH minus can act as a nucleophile, but will haloarenes easily undergo substitution reaction? No, it simply undergoes substitution either by SN-AE mechanism, SN-AE mechanism or SN-EA mechanism. Right now in this chapter mainly we are going to talk about this SN-AE mechanism. So for halobenzene to undergo substitution reaction, one thing is mandatory, that is the presence of electron withdrawing group either at ortho or at para or at ortho para position. So whenever I am having a halobenzene, halobenzene, right? And if there is an electron withdrawing group at ortho position or para position, or at both ortho and para position, and now it's treated with OH minus, this halobenzene will readily undergo substitution reaction, and I will have the formation of phenol. EWG substituted here. As we can see here, I'm having chlorobenzene, and at para position I'm having a nitro group. Now if it's treated with a strong base NaOH, it's nothing but a source of OH minus, and this OH minus will do substitution reaction. I will have the formation of phenol. Since the medium is alkaline, first I will have the formation of phenoxide ion, and which is further treated with H plus / H2O. Finally I will have phenol, students. I hope you understood this one. Okay. Students, we can synthesize phenol from chlorobenzene or halobenzene through one more method, and that process is referred as Dawes process. Let's try to understand that also. Dawes method. Okay. I'm having a chlorobenzene. Now this chlorobenzene is treated with NaOH. There is no electron withdrawing group present at ortho position or para position. So will it undergo substitution reaction? Not easily. So in order to carry out the substitution reaction here, what we provide very high pressure, a pressure of 300 atmosphere and a temperature of 623 Kelvin approx. This is the temperature range and this is the pressure range. So at very high pressure and very high temperature, this chlorobenzene undergoes substitution reaction with OH minus. I will have the formation of phenol. First, I will have the formation of phenol under alkaline condition, acid-base reaction. I will have the generation of phenoxide ion. This phenoxide ion will be treated with acidified water to form phenol. Right? So this is how we synthesize phenol from halobenzene. So there are two methods through which we can synthesize phenol from halobenzene. One, through SNAE. In that particular case, presence of electron withdrawing group is mandatory at ortho and para position, right? And second, through Dawes process. Let's move ahead. We have few more methods through which we can synthesize phenol. This is one of the method. I am having sodium salt of carboxylic acid at para position, and phenol, it's treated with soda lime. Will readily undergo decarboxylation, and finally I will have the formation of phenol along with CO2. Right? This will get released in the form of CO2. Right? So distillation of phenolic acids with soda lime produces phenols. Okay. Next one. And student, this particular method is really important. So let's discuss this particular method. Preparation of phenol from cumene. Okay, what is cumene? Isopropyl-benzene. I'm having pH, CH3, CH3, right? And now it's treated with O2. I'm directly treating with O2, air. What will happen? I will have insertion of oxygen here. Student, what I will get as COOH CH3 CH3, cumene hydroperoxide. Cumene hydroperoxide. Now this one is treated with H2SO4. This H2SO4 is a source of H plus. What it will do? Protonation. Now as soon as it does protonation, what we will have? We will have the migration of this alkyl group to this oxygen, and this will get eliminated in the form of acetone. So first I will have the formation of OH over here, and this one this group will get departed, and it will get departed in the form of CH3 C double bond O CH3. In this particular process, the things which are quite important, first I am having isopropyl benzene. This is isopropyl benzene treated with oxygen, formation of cumene hydroperoxide. This intermediate is also really important, and now this cumene hydroperoxide is treated with an acid. Obviously this oxygen will get protonated. As soon as it gets protonated, I will have bond cleavage. This phenyl will migrate here. I will have positive charge. This oxygen will delocalize, formation of acetone as a byproduct, and this is our main product. So this is how we synthesize phenol from cumene or isopropyl benzene. Now if you look here, what's there? I'm having benzene treated with CH3CH doubly bonded CH2 S3PO4. This S3PO4 will attack here. I will have the formation of carbocation, right? And now this carbocation will do electrophilic aromatic substitution, and finally I will have the formation of this isopropyl benzene. So this step I have written directly from this step, right? This is cumene, isopropyl benzene. This is cumene. This cumene on treatment with oxygen forms cumene hydroperoxide, and cumene hydroxyperoxide on treatment with acid forms phenol plus acetone. I hope you understood this one. Students, now let's discuss some chemical behavior of phenols, or chemical properties of phenols, or we can say chemical reactions of phenol. Student, if I look at the structure of phenol, pH, OH. Can I say this OH will act as a plus M group? So can I say it is a ring activator? This phenol is an activated ring activator, right? A plus M group will activate the ring. So can I say if this phenol is treated with any electron deficient species, say electrophile, that is electron loving species, can I say this electrophile will get substituted at ortho and para position, right? OH, E at here or E at this particular position, right student? So can I say this phenol, whenever treated with an electrophile, the electrophile will get substituted either at ortho position or at para position, right? So now let's study some electrophilic substitution reaction of phenol. Phenol treated with bromine water. Student, this particular reaction is really important. We have two different types of reaction. Phenol treated with bromine in the presence of polar solvent, that is bromine water. In this particular case, the product formed is 2,4,6 tribromophenol. 2,4,6 tribromophenol. Right? Basically, it's also used as a test. Phenol on treatment with bromine water gives a precipitate of 2,4,6 tribromophenol. If this phenol is treated with phenol on reaction with bromine in the presence of non-polar solvent, let's suppose CH2. Same phenol, same bromine, but now here my solvent is CH2. Now in this particular case, all the positions will not get substituted by bromine. Only ortho or only para position will get substituted. So I will have mono substitution occurring here, and in this case, student, either I will get this ortho bromophenol or we get para bromophenol. This one. OH and Br getting placed at para position. So phenol on treatment with bromine in the presence of polar solvent, I will have all ortho and para position getting occupied by bromine. I will have precipitation of 2,4,6-tribromophenol. Phenol on treatment with bromine in the presence of non-polar solvent. Phenol on reaction with bromine in the presence of non-polar solvent. I will have mono substitution of bromine. Bromine will either occupy ortho position or it will occupy para position. I hope you understood this reaction of phenol with bromine water. Next one. Student, here I am having phenol and now it's treated with a nitrating mixture, you can say, or even dilute HNO3. The electrophile generated here is NO2 positive. Simple, phenol is a ring activator and ortho para director. All the incoming electrophile will get substituted either at ortho position or at para position. So NO2 will get substituted at either para position or at ortho position. Now, if we look at this ortho substituted phenol, ortho-nitrophenol, here I will have intramolecular H bonding, right? And if I am having intramolecular H bonding, in that case, the stability will be more. Now, student, one more question is asked. Which one is steam volatile? Ortho-nitrophenol or para-nitrophenol? Student, in case of ortho-nitrophenol, I will have intramolecular hydrogen bonding, whereas in case of para-nitrophenol, I may observe intermolecular hydrogen bonding. Now, student, whenever I am having intramolecular hydrogen bonding, in that case, the surface area of the molecule reduces. Surface area reduces because of ring formation. And if ring formation is there, surface area will get reduced. Because of that, the intermolecular force of attraction will decrease. And because of that, boiling point will decrease. So if someone talks about the boiling point, which one will have higher boiling point? Para-nitrophenol. So which one will be a steam volatile? Ortho-nitrophenol. The one which is having less boiling point. Ortho-nitrophenol will have less boiling point as compared to para-nitrophenol. The reason is intramolecular H bonding. One more thing, in case of ortho-nitrophenol, sometimes people ask, compare the acidic strength. Again, in ortho-nitrophenol, due to intramolecular H bonding, the acidic strength will also be less, right? The H plus leaving tendency will be reduced. Why? Because this H is now somewhat physically bonded to oxygen also. So the leaving tendency of H plus will reduce, and because of that, acidic strength will also be somewhat less as compared to para-nitrophenol. Now, phenol treated with a concentrated HNO3. In this case, we will get a mixture of product. Student, here we will have first, this HNO3 may act as a strong oxidizer, and in this particular case, this phenol will get oxidized to hydroquinone. Second, one more thing, at the same time, we will have formation of 2,4,6 trinitrophenol, and this 2,4,6 trinitrophenol is referred as picric acid. So, phenol on reaction with concentrated HNO3 along with H2SO4 will give first, the major product is the oxidative product. This ring will cleave. I will have doubly bonded O here and doubly bonded O at the para position. That is the oxidative product, and small amount of picric acid is also observed. For examination point of view, you should write only picric acid. Phenol treated with concentrated HNO3 or along with H2SO4, you will write the product as 2,4,6 trinitrophenol, and this 2,4,6 trinitrophenol is nothing but picric acid. Let me write that. OH, NO2, NO2, NO2. Right, students? I hope you understood this electrophilic aromatic substitution reaction of phenol. So shall we move ahead? Student, let's discuss one more reaction, important reaction of phenol, and that particular reaction is referred as coupling reaction. How does this reaction occur? Let's try to understand. Coupling reaction. Coupling reaction. Okay. Student, basically first we are going to take species aniline, NH2. Now this NH2, pH NH2 is treated with HNO2 at 0 to 5 degrees centigrade. The product which we get is diazonium, pH N2, N triple bond N positive. Now I am having diazonium, pH N triple bond N positive, and now if it's treated with nucleophile, we may have two different types of reaction. One, if the nucleophile is a weaker nucleophile, weak nucleophile, Nu minus. In that particular case, can I say before the nucleophile attacks, this one is a very good leaving group. In that particular case, I will have simply replacement of this N2 by a nucleophile, and I will have simple substitution reaction. Right? Why? Because the nucleophile is weak. Before it attacks on this carbon or on this benzene ring, N2 has already departed. So I will have simple substitution reaction. Now, if the nucleophile taken is a strong nucleophile, in that case, what will happen? This nucleophile will attack on the nitrogen part itself. As soon as it attacks on this nitrogen part, this bond will shift over here, and I will have the formation of pH N double bond N Nu. Let us try to understand the second reaction. Okay. Student, I am having diazonium salt, right? N triple bond N positive. And now I treat it with phenol in alkaline medium, NaOH. Why I am taking alkaline medium? Can you tell me? pH 9, pH greater than 9. Why I am taking this alkaline medium? The basic purpose of taking alkaline medium is to make this phenol as phenoxide ion, and this phenoxide ion will act as a strong nucleophile. Anionic species are a better nucleophile than a neutral one, right? So first I will have the formation of phenoxide ion, pH O negative, right student? Now this phenoxide ion can undergo resonance, and I will have the formation of, I can write it like this, right? This one will delocalize, so, and this one. I hope you understood this one. No problem. Through resonance, we can move here, right? Now, it will attack on N triple bond N positive, right students? Okay. Now, how will the reaction occur? Can I say this C negative will act as a better nucleophile? It will attack here. As soon as it attacks here, this particular bond will shift over here. So I will have P, this ring, doubly bonded O, and now to the para position, it is connected to N, doubly bonded N, connected to a pH. Right student? Now it is having one acidic hydrogen, will undergo aromatization, and finally I will have phenol, and on this phenol at para position, let me draw it in a better way. On this phenol at para position, I will have N double bond N pH. Generally, coupling occurs at ortho and para position, and more preferably at para position. If para position is blocked, then the coupling will occur at ortho position, but preferably at para position. Now, lot of questions may come to your mind after seeing this reaction. Sir, why I am doing resonance and all these things? This O minus can also act as a strong nucleophile. Why I am doing resonance? Why I am attacking from C side, not from O side? Student, I am having phenoxide ion, and then through resonance, basically I am generating C minus. Between C minus and O minus, can you tell me which one is a better nucleophile? C minus, lesser the electronegativity, better is the donation ability. So this C minus will act as a strong nucleophile, and what this strong nucleophile will do, it will attack on nitrogen. Then as soon as it attacks on nitrogen, the pi bond will shift on the next nitrogen. I will have N double bond N, right? Now you will say, so here the product is not aromatic, but here you have written phenol. Yes, because we have studied para-tautomerism. Here one acidic hydrogen is there. This hydrogen will oscillate, will go to this oxygen, and I will have my aromaticity regained. Right, student? So whenever I am having phenol treated with diazonium salt in basic condition, this reaction will occur only in basic medium, not in acidic medium. This in acidic medium, the coupling reaction won't occur. In that particular case, simple substitution reaction will occur. N2 positive will get replaced by phenol itself. Am I clear? Because in acidic medium, that nucleophile will be a weaker nucleophile. So if diazonium salt is treated with any weak nucleophile, let's suppose water, I will have the formation of phenol, right? But if diazonium is treated with a strong nucleophile, I will have this coupling reaction, diazo salts. Right? Students, I hope you understood this one. Please copy it. So now let's move to the next important reaction of phenol. And student, believe me, this is also one of the most important reactions, Reimer-Tiemann reaction. Lot of time questions are directly asked from this particular concept. I'm having phenol. Phenol is treated with CHCl3 chloroform in the presence of NaOH. What this CHCl3 will do? It will react with NaOH. I will have the formation of CCl2 dichlorocarbene as the electrophile. So student, in Reimer-Tiemann reaction, the real attacking electrophile is dichlorocarbene. Carbon connected to 2 halogen, 2 chlorine, and 1 unshared pair of electron. Am I clear? Dichlorocarbene. The carbene which we form here is basically a singlet carbene, right? So both the unshared pair will be there in one, and like this, I will have one completely vacant p orbital, right? Now it's an electrophile. I'm having phenol treated with any electrophile. I will have electrophilic aromatic substitution, and the electrophile will attack at ortho position and para position. Right, student? Now, can I do one more thing? Phenol with NaOH, can I say, will it form phenoxide ion? The answer is yes, definitely. Now, let me do one. Can I write it like this, student? Doubly bonded O negative, and like this. And now can I say this electron rich species will attack on the electron deficient species? Right? Why it is electron deficient species? 6 electronic species. Okay. Octet incomplete. Now I will have the formation of pH, doubly bond O, C, Cl, Cl negative, right? It has accepted one electron. Now I will have a negative charge over here. Can I say I'm having one acidic hydrogen over here? What this carbon ion will do? It will snatch this acidic hydrogen. As soon as it snatches this acidic hydrogen, I will have the formation of CHCl, Cl, negative doubly bonded O. Right, students? I hope I am clear till here. Am I clear? Now, simple resonance, formation of phenoxide ion. O negative, CHCl, Cl. Now you treat this species geminal dihalide with water. You do hydrolysis. You will get, you're having pH O negative, CHCl and Cl. It's treated with H2O. Put one hydrogen over oxygen and replace this chlorine with OH. So you will have OH, CH, OH, OH, geminal hydroxyl system. Readily undergo dehydration. I will have removal of one water molecule and I will have the formation of OH and C double bond OH. Right, student? This is one of the product. We can have one more product. How? Let's see. This negative charge can get delocalized and it can come to para position also. So this, the electrophile, real attacking electrophile, which is carbene, will attack here also, right? And then I will have the same repetition. So can I write the product directly? I will have one of the product as para-hydroxybenzoaldehyde and the first one is ortho-hydroxybenzoaldehyde. Now you may say, which one is the major one? Student, this is major one. Why? Because in this particular case, I will have IMHB, intramolecular hydrogen bonding, and because of intramolecular hydrogen bonding, stability will be more. The one which is more stable is always the major product. So this one is major product. Students, if we look at this Riemann-Tiemann reaction, I am having phenol. This phenol is treated with CHCl3, right? CHCl3 in the presence of a base. Now the base we can take is either NaOH or KOH. Now there is one more interesting story about this base also. And the product which we write is this one, right? OH and C double bond OH. Let's talk about this ortho itself because this is the major one. Now student, if I take this NaOH as a base, can I say I will have phenoxide ion, O negative. This O negative will get connected to Na positive and now I will have C double bond OH. So I will have a sort of ring formation here. And now if I take this KOH as a base, in that particular case, I will write my product or I can write my TS as like this, C double bond OH and K positive. Now, a very interesting story here. Student, if we look at the size of Na plus and if I look at the size of K plus, which one is having larger size? K plus. Larger the size of cation, lesser will be the stability of this ring, right? Since Na plus is smaller in size, smaller size of NaOH will, or Na plus, not NaOH, Na plus will stabilize TS in a better way as compared to K plus. So students, if we are asked or if we are having a preference to choose between the bases NaOH and KOH, which one will you choose? NaOH. Why? Because here smaller size of cation, I I will have better interaction, I will have a more stable ring formation, I will have a more stable transition state, and because of that the stability will be more, the product yield will increase. So NaOH is more preferred over KOH in Raman-Diamond reaction. I hope you understood this one also. So shall we move ahead? One more application, I'm having phenol. Now this phenol is treated with CCl4, right? So what this CCl4 will do? Here in this particular case, instead of getting aldehyde, we get acid. So we get salicylic acid as the major product, orthosalicylic acid, and then this one as para-hydroxybenzoic acid as the minor one. In this case, I will have intramolecular hydrogen bonding. Because of that, because of IMHB, stability will be more, right students? Okay, so shall we move ahead? Yes. Phenol treated with CCl4 in the presence of NaOH. First I will have the formation of CCl3 here. Now all the chlorine will get replaced by OH. So carbon having 3 OH. I will remove one water molecule. Aldehyde containing OH is nothing but carboxylic acid. Shall I write that? Okay. OH, Cl, hydrolysis. Simple. OH, better write O negative here, and then C double bond O, OH. Right student? So in this particular case, salicylic acid will be the major product. Let's move ahead. Coal-base carboxylation reaction. Students, once again I am having phenol. This phenol is treated with OH minus. Phenol, as soon as treated with OH minus, will generate phenoxide ion, acid-base reaction, right? Phenoxide ion, through resonance, I will generate this one. Now it will attack on the Lewis acid CO2. And I will have the formation of double bond COO negative. Right students? One acidic hydrogen, tautomerization, right? And then I will have the formation of OH, C double bond O negative. Obviously now I am going to put HCl. I will have the formation of, once again, salicylic acid, that is orthohydroxybenzoic acid. Even we can, here also we can get para-hydroxybenzoic acid through resonance. This negative charge will delocalize here and will come at para position. Now this will attack at para position. So I will have two products, but the ortho substituted benzoic acid is going to be the major one. I hope you understood this one also. Please copy it. Student, we have one more reaction, and this particular reaction of phenol is referred as price rearrangement. Okay. Phenol is treated with CH3 C double bond OCl. Okay, let's first of all talk about this. Alcohol treated with this one, CH3 C double bond OCl. What I will have? Can I say? We have studied this reaction, right? This alcohol will attack here. As soon as it attacks over here, the pi bond will shift over here. I will have the formation of ROH positive, CO negative, CH3 and Cl. Student, now this one will delocalize, this one will depart, and then this one will also depart. So I will have the formation of ROC double bond O CH3. Formation of ester. So here also I am having formation of this phenyl ester. Now this one, whenever treated with a Lewis acid AlCl3, I will have simply remove this one and substitute this one as, consider this one as the electrophile. From here we generate electrophile. Put one hydrogen here. Now it's phenol. Electrophile will attack at ortho and para position. Simply attach it at ortho and para position. I hope you understood this one also. Please copy it. The next reaction, phenol treated with zinc dust. Simple, remove OH. Phenol treated with zinc dust. You simply need to remove this one and form benzene as the final product. Am I clear? So phenol on treatment with zinc dust gives benzene, the most easy reaction of entire organic chemistry, right? Shall we move ahead? Okay. Student, now it's time to discuss some important tests of phenol. The first test which we are going to discuss is litmus test. Students, we have already studied aromatic alcohols are more acidic as compared to aliphatic alcohol, and the reason is the conjugate base formed in case of aromatic alcohol is more stable, a resonance stabilized species, right? So if we do the litmus test here, what will happen? The blue color of the litmus paper will turn red. Why? Because phenol is having acidic behavior. So phenol turns blue litmus to red. Phenols behaves as an acid because of the presence of polar OH group in them. They ionize in aqueous solution to generate phenoxide ion, right? A source of H+, stronger acid as compared to aliphatic alcohols. We have one more test, and that is FeCl3 test. Student, whenever this phenol is treated with FeCl3, we get a violet coloration, violet complex formation. And suppose if a solution is there, we don't know whether the alcohol is aliphatic alcohol or aromatic alcohol. I don't know about the nature of alcohol. I'm not sure whether it is an aliphatic one or aromatic one. Now, but if I put FeCl3 over here, and if I get violet color complex, it indicates it confirms the presence of aromatic alcohol. So phenol, whenever treated with neutral FeCl3 solution, we will have a violet coloration, and it indicates or it confirms the presence of phenol. Students, that's it for today's class. I hope you have enjoyed this particular class. Students, because of time constraints, we could not do more questions in case of phenols, but don't worry, we'll have a complete live session where we'll be solving at least 30 questions related to phenol and ether. So you don't need to bother about the question segment. We'll have a separate live class for this question segment. If you feel any difficulty in any part, please do mention in the comment box. I'll be very happy to solve your query. Thank you, students. Thank you all for watching the lecture.